presentation file in the Zoom window. But anyway, okay, we got the acknowledgement that we're live. So we'll go ahead and get started. Welcome everybody to the 2022 Ocean Model Working Group Winter Meeting. My name is Brian. I'm the NCAR co-chair. And we also have this morning Ian Grooms, who's our external co-chair. So we've got about 2.5 days of sessions. We've broken it up into about 2-hour sessions, AM and PM. Generally speaking, we have model analysis and diagnostic kind of talks and model development type talks in the afternoon, with some accommodation for people in remote time zones. So yeah, so let's we'll go ahead and get started here in just a second. Let me just go over some of the logistics one more time in person. Let me share again. So first of all, we encourage and expect a respectful scientific discourse during the working group meeting. So please follow our CGD guidelines for constructive meetings. Let me back up. During the meeting, all talks will be 20 minutes with 5 minutes for questions and discussion. Please keep your microphone and cameras turned off during the talks. You're welcome to turn them back, the cameras back on during questions. And to indicate you'd like to ask a question, please use the raise hand feature in Zoom, and whoever is moderating that session will call on you when you're up. For speakers, please, in order to keep us rolling, please have your presentation file open and ready to go a couple minutes before your scheduled time. And we'll have you, unless you have indicated otherwise, we'll have you run your own slides and share screen during your talk. Other logistics, please send a copy of your slides, PowerPoint, Keynote, PDF, whatever, to Elizabeth at fair@ucar.edu, preferably before your presentation, so we'll have it as a backup in case there's some sort of connection issue, and also so that we can post it to the meeting website for reference for the participants later. As well as this live Zoom meeting, you can watch the presentations on the CGD YouTube channel live and also later on demand. Finally, we have about 20 to 30 minutes of open discussion time at the end of each day. So that can either be used to revisit presentations during the day, and also to discuss issues of interest and of things that the working group should be addressing, things that you think we need to be looking at or working on over the next months and year to advance the interest of the working group, as well as make sure that we're working synergistically with the other CESM working groups and with the rest of the MOM6 ocean modeling community. So if you have suggestions for topics, broad topics or not so broad topics you'd like to see us address during the discussions, either indicate that to Ian or I through the chat in the meeting or through email. So let's see. So we've got fairly brief, well, maybe somewhat shorter sessions today, and we're going to get started with a couple of talks on high latitude shelf processes. So Teresa Morrison, are you ready?
Yes, I am. Okay, sharing my screen.
Yeah. Okay,
Great.
go ahead and take it away. Introduce yourself and take it away.
Awesome. Yeah. So my name is Teresa. I am a graduate student at the Scripps Institution of Oceanography. I work primarily with Julie McLean and Sarah Gilly, and today I'm going to be presenting some results from high resolution ocean models we've used to study the difference between surface and vertically distributed meltwater forcings from the Greenland ice sheet. Oops. My computer doesn't want to go to the next slide. There we go. Our motivation from this is to better understand the role that the increased mass loss from the Greenland ice sheet, primarily through runoff, will have on the shelf exchange and local circulation in the subpolar North Atlantic. So the projections all show accelerated mass loss and increased sea level rise contribution from the Greenland Antarctic ice sheets in the next decades and next century. But our question is really focusing sort of on the processes that how that meltwater is added to the model affects. So how the shelf dynamics change. We are using the Bamber 2018 meltwater data set. So this is a product that's based on an atmospheric reanalysis and was used to develop a mass budget for the Greenland ice sheet. And there are two primary components that you can see on this plot: the solid discharge, which is in the sort of fuchsia color, and the red line, which is the runoff. And starting in the late 1990s, they both sort of increase through the end of the time series. And that leads to an increase in the total freshwater discharge from the ice sheet. Note that the total freshwater flux is on a different scale than the rest of the lines on this plot. And this runoff is entering the ocean in this critical region in the North Atlantic where we have deep water formation. And so we're interested both in how that meltwater gets transported into the Labrador Sea, along with our concerns about it bringing more warm water onto the shelf and modifying the shelf circulation. One key part of that is, of course, how it is added to the models. So many previous hosing or Greenland freshwater perturbation experiments just add meltwater to the surface layer of the models, much like you might with a river. And this can create a very fresh surface layer, and it doesn't take into account the mixing that occurs within subglacial fjords or glacial fjords, which are very dynamic, but very small, maybe less than 10 kilometers wide and long. So they're sort of unresolved by a typical global model. But they have subglacial discharge plumes, interfacial mixing from internal waves, entrainment along sills that have been shown in observations to dilute meltwater before it reaches the continental shelf. So we want to represent all of this mixing that occurs within fjords in a very simple way by vertically distributing our meltwater forcing in our simulations. So with these simulations, we have a few key questions that I'm going to lay out before we talk about what the setup is. So first is the sort of long-term changes in shelf heat content and the potential for increased ocean-driven melting as freshwater flux from the ice sheet increases. And then the dynamic part of that is the changes in cross-shelf exchange and along shelf currents, particularly in the West Greenland Current and West Greenland Current eddy shedding regions in the Labrador Sea, which is where previous studies have shown a lot of this meltwater is ejected into the Labrador Sea. And then the most important question, I think, for the community is whether the vertical dilution of meltwater makes the simulations more realistic, and if the difference between a surface and a vertically distributed meltwater simulation is actually statistically different, and therefore if this is sort of an avenue to pursue of the improvement to meltwater forcings. Fortunately, that's a bigger question that I haven't fully tackled yet, so it's a to be figured out later in this work, but I'm going to focus on the first, or the middle one primarily today. So this is a little bit more of a description of what a meltwater forcing actually looks like. It's based on the Bamber 2018 data set, and it's remapped point by point to our nearest ocean grid cell. The data set is monthly in time, so we linearly interpolate, and we use a Gaussian filter to do some minimal spreading, but we keep the meltwater forcing relatively coastally trapped by not having any freshwater extend to regions that are deeper than 400 meters. The schematic on the right shows what the vertical distribution is. So we just use a vertical uniform distribution over 200 meters, and then there's no meltwater added below that. The alternative is the surface case, where roughly the top 10 meters is our surface layer, and it just gets added to that. The big picture of this model is it's a global POP2 CIS5 model that we use the Core 2 interannual forcing for. We start our spin-up period in 1975 with no meltwater and use 60 vertical levels in our vertical resolution Z coordinate. There's meltwater from Greenland, but there's also meltwater in the Southern Ocean, but I'm not going to talk about that today. And this is a comparison of the grid scale between the typical 1/10 tripolar grid and our ultra-high 8-to-2 grid. So we have a grid resolution that's closer to, say, 3 to 5 kilometers in our Labrador Sea subpolar North Atlantic area of interest, compared to something in the range of 6 to 8 in the 1/10 degree. I'm going to talk about the 3 cases we've run today, which include a control case that has no meltwater added. It's just a continuation of our spin up. The surface case, which was branched from the spin up run in 1990. And then the spread case, which is our sort of main run that we are hoping to continue through the end of the Core 2 forcing, possibly transitioning to JRA later. But I'm mostly going to focus on the 1992 comparison year. Just to give you an idea of what the global statistics of this model is, this is sort of the RMS sea surface height to see what sort of eddy activity we have in this model. In particular, in the subpolar North Atlantic, we have high RMS around the northwest corner and a fairly active subpolar North Atlantic in general. If we zoom in particular on the Labrador Sea, we can make a comparison to a similar 1/10 degree run, which is the panel on the far left. And I'm looking at the surface eddy kinetic energy in these 2 plots based on the 1992 daily averages. So in our ultra high control case, we have both a sort of broader swath of eddy kinetic energy, and it extends further south into the Labrador Sea, which is consistent with some satellite-based observations of the sort of general structure of the elevated eddy kinetic energy that's associated with eddy shedding in this region. For water mass comparisons, we have started by looking at the AR07 repeat hydrography line because it has a time range that's similar to our observations. We made some comparisons to OSNAP, but the sort of multi-decade variability seems to be a bit more of a cause of difference than just validating our simulations. So this is a comparison of the spread case, which is the blue points, and the observations in black. We can identify a few different water masses here. Our Atlantic origin waters are somewhat warmer than the observations, which could be also what is causing our Northeast Atlantic deep water or Denmark Strait overflow water to also be warmer. But the Labrador coastal water, which is along the Labrador shelf, is fresh and cold in both model and observations. So this is just sort of a basic starting point for looking at the validity of our models. I'm going to switch now to talking about some of our results. So first I'm going to show some of the meltwater tracer videos to look at the horizontal and vertical pathways in the Labrador Sea, and then show one specific example that connects the change in isopycnal slope at the shelf break to the presence of meltwater. So this is a GIF that is not playing because this is a PDF. I'll just switch presentation mode really quick because I didn't think that through. Okay. So this is showing the, nope, that wasn't it. Anyway, this is fine. This is showing the meltwater concentration in the upper 200 meters in the last month of our comparison, which is December 1992. And we can see eddies shedding from the West Greenland Current and the sort of increase in presence of meltwater on the Labrador Shelf in the surface case, which is the bottom panel. If we look at the below 200 meters but above 2000 meters layer, note that the color bar has changed here, which I'm sure you can't see because it's so low, so small anyway. Okay, there you go. So the color bar is an order of magnitude less. We see the sort of logarithmic drop off in the amount of meltwater tracers we go to depth, but there's the same pattern of eddies of the meltwater shedding off the coast and entering the Labrador Basin, much stronger in the spread case compared to the surface case. And if we look at depth, we see the same pattern where, again, this is 2 orders of magnitude lower on the color scale, but there's quite a bit more dye tracer in the spread case.
Teresa,
Yeah.
We're only seeing the 2 leftmost panels on your slide.
Okay. Oh.
What you're intending.
Yeah. How about, okay, sorry. What do you see? Do you see all 3 now?
6 panels, yeah.
Okay, great. So this is the video. Yeah, this is the movie of them moving. Lots of eddy activity. This is the still where you can see the increase in meltwater on the shelf in general in the surface case, and then more entering the basin in the spread case. I've done some control volume analysis as a part of looking at our cross-shelf fluxes. So the surrounding shelf plots, which are on the left, are, sorry, on the top row, are the sort of Labrador Shelf and West Greenland Shelf combined. And in that case, we have more meltwater in the surface case throughout the year. And then in the Labrador Sea, we have the opposite, which is more meltwater in the spread case in the surface. So we are seeing more meltwater being transported into the Labrador Sea in the surface case, or in the spread case. But it's not uniform throughout the year. There's some sort of seasonal cycle to when it occurs where the amount sort of catches up and then diverges again. Of course, this is still a relatively small amount of fresh water, so we need to consider what impact it might have on salinity. In both regions, the freshwater cases are in general fresher than the control case, which makes sense. The exception is in the sort of late summer, fall months in the Labrador Sea, where the surface case is actually more saline than the control case, which is really interesting, not necessarily what you would expect, but it might show some blockage of the source of surface salinity in that region because of how the meltwater is added. It's for further exploration. So this is going back to the eddy kinetic energy and looking at the structure of the currents at the shelf break. So I've taken that region of elevated eddy kinetic energy in the control, which is relatively similar between the surface and the spread case. Stronger core, we could say, in the spread case, but with just a year, it's hard to know what's model variability versus a real difference in the simulations. And I've taken this transect right through it. And along looking across the shelf break, we can look at the salinity in the surface, spread, and control cases. And I've also plotted the isopycnals, in particular the 27.5 isopycnal is the solid black line here. The slope of the isopycnals at the shelf break is similar in the surface and the control cases, but note that the 27.5 isopycnal does not outcrop in the surface case. There's this sort of fresher layer that extends farther out into the basin. In the spread case, the isopycnals are much flatter than the other two cases, and the 27.5 isopycnal does outcrop, but it's further offshore than it does in the control case. If we look at the salinity differences, it's about what we would expect. The spread is much fresher than the control throughout that entire region. The surface case is fresher in the basin compared to the control, and that difference just stacks in the difference between the spread and the surface. So the spread case is more saline in the basin compared to the surface in this one particular slice along the shelf. And can this be attributed to our meltwater forcing? So if we compare that to both the presence of meltwater on the shelf, which is our dye tracer in the top two panels, and the difference between the spread and the surface, we see that there's more dye tracer in the spread case where it's fresher than the surface case. So, oops. The takeaway from this is that the isopycnals are flatter in the spread case. This corresponds to freshening across the shelf break, and the freshening is co-located with the meltwater tracer. So while the meltwater perturbation is small, it seems to be changing something in how the isopycnal structure and possibly cross-shelf exchange are set up between the surface and the spread cases. So just as a summary, what we have looked at is how the vertical distribution of the meltwater from the Greenland ice sheet influences how it extends into the Labrador Sea. We want to understand what mechanism is causing the change in cross-shelf exchange. And so I've started looking at that with these sort of cross-shelf transects and control volumes, but want to get more into like dynamics of looking at the changes in available potential energy and the cross-shelf density gradients, and then diving more into what the implications are for freshening in the Labrador Sea, and in particular, what would occur if this meltwater really ramped up as it's projected to in future decades. And also with our longer time runs, the potential for warming on the continental shelf, because the warm water on the shelf is one source of ocean-driven melting for the ice sheet. So will the ice sheet sort of accelerate its own melting? And then the main question that needs to be addressed is how vertically diluting the meltwater changes the simulations relative to observations. Are we getting closer to what we see in observations, or are we not improving the validity of the model? So you can find out more about this. I'll be presenting similar work a little bit further along in my ocean modeling or ocean sciences meeting presentation. So this is the section information in my title. So I'm a little bit early, but I can take questions.
Okay, thanks, Teresa. Questions for Teresa?
Yeah, thanks, Teresa. So Greenland discharges fresh water both as liquid, but it also discharges it as icebergs. And like ice fronts, icebergs also melt at depth. But you were finding some things that were a little bit counterintuitive in some of your results when you distributed the fresh water at depth. Have you thought at all about whether if the discharge is as icebergs that drift away and then discharge at depth, you might get different results than if you're just putting in the fresh water distributed over depth in the fjords themselves?
Yeah, that's a really good question. So we did just merge the solid discharge and liquid runoff from the Bamber data set into one term that we added. So we didn't take into account iceberg drift or anything. And part of that was not having a good idea of the residence time of icebergs in fjords and how to sort of estimate that. I think that it's definitely a really good question. And I think something would be really interesting to do with this model would be to add sort of a Lagrangian particle to track where icebergs might go and use that to inform where to add that meltwater in the future, because that was something else that we also weren't as sure of. But yeah, it's a good question.
Okay, Mehmet?
Hi, sorry, just to make sure if I understood correctly, you use the vertical distribution all over the Greenland as uniform. Is that the case?
Yes, that's the case.
And is that realistic in a sense, or is it generally in some fjords where there is particular ice sheets that does this melting?
Yeah, so there are some places where this might be not as clear of an estimate. There aren't a ton of observations of the vertical distribution of meltwater or fjords around Greenland. I worked with Frank a little bit to come up with a very simple box model that one could use to estimate how far that vertical distribution should be based on the amount of freshwater going into a particular fjord. But this was our sort of first stab at, does this make a difference? What's something simple we can do?
Okay, thanks.
Peter.
So if you go back to the slide with the sections of the across the lab sea with the isopycnals.
Yeah. This slide.
That one. So yeah, the ones on the left, I mean, that does seem quite a large change. So can't you compare that to observations across that section?
Yes. So this section is not the AR07 section. It's a section I sort of chose to cut right through the eddy kinetic energy region. So I don't know if there are observations directly in that area. I do want to look at the Pallas floats and some of the other observations that were taken at this time, which might include something that's closer to this high eddy activity region. It is a big difference though between the two.
Yeah, well, perhaps you could do the same across the line that is the WOS section, and then that would directly compare with some observations.
Yes. I think it's a question of whether where we see the most changes. I mean, I picked this region, this area specifically because I thought that might be where we'd see a big change. So definitely looking across the WOS is the next step.
Okay, Keith, a short question.
Teresa, that was really interesting stuff. Thanks for sharing that with us. Have you also considered the heat fluxes associated between the seawater and the ice and how that affects the density structure of the ocean?
Yeah, so our meltwater forcing is just a virtual salt flux. It doesn't have any associated heat flux. And part of our reasoning for that is because much of the melt occurs over the surface of the ice sheet. So that's heat flux to the atmosphere. But it's a great question. And I know that like the JRA forcing that includes this meltwater does include a heat flux in certain setups. So it's definitely something to look into.
Okay, great. Thanks, Teresa.
Mm-hmm.
We'll move on to Rebecca Beedling. We'll switch hemispheres.
All right, can you guys hear me?
Yep. We see presenter mode.
Switch this. Swap displays. Okay, is that better?
Yep, looks good.
All right, yeah, so thanks for giving me the opportunity to give this talk. So we're gonna switch hemispheres and I'm gonna focus on understanding the Southern Ocean response to both ice sheet melt and wind stress change using two different GFDL coupled models. And I hope to convince you by the end of this talk that resolving the Antarctic slope current around the Antarctic continental shelf is really important to explaining the diverging model responses that we found. And this work is currently in revision in JGR Oceans, and I'm only going to focus on a subset of the results here, focusing on the Antarctic shelf. But we also found really interesting results in the surface response, et cetera. So if you have any questions or you're interested in the further details, feel free to reach out to me, and I'd be happy to share kind of the more details of this work. So when we think about what's happening in the Southern Ocean right now and what's projected to continue throughout the 21st century, there's two major changes that are happening. First, we're having increased melting of the Antarctic ice sheet, which is delivering vast amount of fresh water to the upper ocean. And then we're also having a strengthening and poleward shifting of the Southern Hemisphere westerly jet, which is shown over here in the right-hand panel, which under a high emission scenario, the jet over the Southern Ocean is projected to both shift poleward and intensify or strengthen. And we care about these two changes for two reasons. First of all, both winds and meltwater, by impacting both the momentum and the buoyancy at the ocean surface, impact ocean ventilation. So they impact how the ocean and the atmosphere communicate with one another and exchange tracers. And thus this impacts oceanic carbon and heat fluxes and their subsequent storage in the ocean. So we really care about this for constraining future climate change. And also on top of that, both winds and meltwater influence the properties on the water of the Antarctic continental shelf. And these waters directly interact with ice shelves. And thus changes in these forcings may lead to important feedbacks that control the future stability of the Antarctic ice sheet. And that's a really large source of uncertainty in understanding future climate, how the Antarctic ice sheet is projected to evolve. So thinking about these two forcings, what insight have we gained from modeling studies on how the Antarctic shelf regime responds to both wind and meltwater perturbations? So as far as wind stress perturbations, considering both a poleward shift and intensification or strengthening of the Southern Hemisphere westerlies, there have been many different studies that have studied this using different methods, different shifts of the winds, different strengthening magnitudes of the winds, but they all show this robust response that as you shift the westerlies poleward and intensify them, you warm the Antarctic shelf. And this is done because you actually increase the access of warm circumpolar deep water that sits offshore. You allow more of that to access the shelf by changing the slope of the isopycnals. So the wind stress actually acts to shoal them as you reduce your easterly stress over the continental slope by pushing the westerlies southward. And this was shown nicely. This is just one example of a study in a 1/4 degree MOM ocean sea ice model by Spence et al. In 2014, where they shifted the westerlies poleward, and you clearly see these large warming anomalies trapped southward of the 1,000-meter isobath, which is on the continental shelf. And importantly, these results are robust across model resolution. So there have been several other studies that have looked at this in a 1-degree model, for instance, Bronsler et al. In 2020, using GFDL's ESM2M model. And then a recent study by Purig in England looks at the relationship between southern annular mode changes and projected changes in shelf bottom water properties. So this is a generally robust response. You shift the winds, you intensify them, you warm the shelf. But when we look at the literature and what it says for how the shelf responds to Antarctic meltwater, we actually see some conflicting results. So there are a number of studies, this one I'm highlighting by Bronsler et al., which suggests that as you increase the meltwater coming off the Antarctic ice sheet, or in this case, not increase it, but actually add it to a model because it's missing that in the RCP 8.5 projections, it leads to this strong warming, the circumpolar warming of the shelf waters, so right against the what would be ice shelves. But more recent studies, this study by Mormon et al. That came out last year, they're using a 1/10 of a degree ocean sea ice simulation. They impose meltwater perturbations, and they see a more non-homogeneous response, where actually in some regions, increased melting of the Antarctic ice sheet can actually lead to strong subsurface cooling, and in this case, along West Antarctica. And then in other regions, such as the Ross Sea, you actually have a very strong warming. So in general, when you look at the literature, coarse ocean horizontal grid spacing models, which I'm just going to refer to here as models which have a grid spacing of a degree or higher, that leads to warming of the Antarctic shelf. But fine resolution models, which generally I'm going to say less than 1/4 degree, show this inhomogeneous response using these two studies as examples that I just went over. And the important thing here is that the coarse resolution models, by showing this strong subsurface warming circumpolar around the Antarctic shelf, imply a positive feedback that would accelerate melt if this were coupled to an interactive ice sheet model. You warm the shelf more, you would lead to more basal melting of the ice shelves. And in the case of the higher resolution model, we actually see a significant portion of the shelf that would imply a negative feedback, where the subsurface cooling may actually work to decrease melt in West Antarctica. So these are big implications, these feedback, for understanding things like how the Antarctic ice sheet will contribute to things like global sea level rise and regional sea level rise. So what we did is we performed a series of simulations using GFDL's CM4 model, which has 1/4 degree ocean grid spacing, and GFDL's ESM4 model, which has 1/2 degree ocean grid spacing, where we impose both meltwater and wind stress changes. And these are imposed at magnitudes that may be expected by near middle of the 21st century. And we do this in a pre-industrial control background state. And our goal here is to understand robust model responses to these forcings. And if we saw diverging model responses, what are the potential processes or mean state biases that may contribute to that? So we performed 3 experiments. The first one, which I'm going to call stress, where we simply impose a FAF stress perturbation, so a perturbation in the zonal and meridional wind stress forcing. Then we have our Antwater simulation, where we're imposing a temporally uniform freshwater flux. And we do impose this at the ocean surface, and this is in regions of observed ice shelf melting. So we don't impose a spatial uniform flux, but we scale this up to a total freshwater flux of 0.1 sphere drop coming off the Antarctic continent. And then we have our combined forcing, where we impose these 2 forcings simultaneously together. And in the interest of time, I'm just going to focus on the combined forcing here, but I want to emphasize that the shelf response in general is really governed by the meltwater perturbation as opposed to the wind stress. So one of the most striking differences we found is that CM4 and ESM4 really differed in their subsurface shelf response. So this is the depth average response from 200 to 1,000 meters along the shelf. And you can see contoured here is a 1,000-meter isobath, which represents basically the continental slope, so the boundary between the shelf and the open ocean. And in CM4, we found this very strong subsurface cooling anomaly that basically extended throughout West Antarctica. And in ESM4, we found actually very strong subsurface warming anomalies in that same region, again, right up against where these ice shelves may be. In our CM4 results, the first thing when I looked at these results, the first thing that stuck out is that they look very, very similar to the 1/10 of a degree simulation by Moorman et al. In 2020. So it seemed like the 1/4 degree model was responding more like these finer resolution models to similar meltwater fluxes. So then looking at the subsurface salinity response, there is a clear striking difference here in that in CM4, we got this very strong freshening that was very homogenized and trapped on the shelf. So we can see these large salinity anomalies are really trapped southward of that 1,000-meter isobath. And in ESM4, that is not the case. We actually have a thermal response that matches somewhat of the, salinity response that matches somewhat of the thermal response, where in West Antarctica, we're actually getting salinification and freshening in other regions. So this was an indication that there must be some sort of process represented differently or acting differently in these models that is controlling the ability of the freshwater to enter the open ocean as opposed to being trapped on the shelf. So the key component that we found that contributes to this and explains this discrepancy in response to the freshwater forcing is the model's ability to represent the Antarctic slope current. So what the Antarctic slope current is, it's this near circumpolar feature that runs right along that 1,000-meter isobath. So it runs right along the boundary between the shelf and the open ocean. And you have these really strong lateral or cross-shelf density gradients that exist. And that allows the establishment of this westward flowing current. which is in reality is absent along the West Antarctic Peninsula and the West Antarctic region. That region is actually dominated by eastward flowing ACC, and circumpolar deep water can readily access the shelf from that region, where in the other regions, as the slope current builds in strength, it provides this strong dynamical barrier for the exchange of properties between the shelf and the open ocean. So let's take a look at how this is represented differently in the mean state in these two models. And just for reference, over here on the left is the Southern Ocean state estimate. And in the middle, you can see CM4, and on the right, ESM4. What you're looking at is the upper 500 meter speed. And you can clearly see these regions of high speed right along that 1,000-meter isobath. And what that is the Antarctic slope current. So that is a strong westward flowing current running along that continental slope. And you can see that generally this structure, if we look in the upper 500 meters, matches roughly that of Saucy. In ESM4, we see a very weak flow. You can see these regions of high speeds along in the South Indian Ocean, but really for the majority of the region, we're not seeing this tightly confined and strong westward transport. And you can see that also if we look at a cross section where CM4 has this well-defined vertically sheared jet that goes to the bottom of the ocean. And in ESM4, you kind of get this broad, weak, diffuse flow. And you end up with a transport that is roughly half of that at CM4. And again, the transport, it differs in different regions around the coast, but in this case, this would be 20 east. This is a region where we would expect the slope current to be in one of its highest states or its strongest states. So what happens is that in the mean state, we have a much stronger slope current and well-defined slope current in CM4. And as we impose this meltwater forcing, that slope current acts as that dynamical barrier, and it traps that freshwater towards the coast. And as you're trapping that freshwater, you're increasing your cross-shelf density gradients. And this leads to a strong acceleration of the flow in CM4, which you can see here in the 500 meter speed anomalies, this dark red region. So we're leading to an acceleration of that flow as the shelf is freshening. So we get a feedback there that we don't really have in ESM4. We do see some signs of it. We do see a intensification in some of these regions along the coast, but it's much weaker than the response in CM4. And the panels up on the right, on the left and right on top of the polar projections are showing that transport at 80 degrees west, which is right kind of in the center of the West Antarctic region. And this region in the pre-industrial control, as I mentioned, is dominated by this eastward flowing jet associated with the ACC. But when we impose these meltwater perturbations, we actually in CM4 see a flow reversal in the West Antarctic region and acceleration of the coastal current. So we go from a region where circumpolar deep water could readily access the shelf to establishing a westward jet, which essentially shuts that off, or it leads to this, what I would call an isolation mechanism, where now we have this barrier between the shelf and the open ocean. That's not the case in ESM4. We don't see a strong minute acceleration, and we do not see a flow reversal. We do see a weakening of the ACC, but no flow reversal as what we saw in CM4 in this region. So this development of this westward flow along the West Antarctic region causes an isolation of West Antarctic shelf waters from that warm circumpolar deep water located offshore. And what happens is we go from a region of upward sloping isopycnals to a region of sharply downward plunging isopycnals. And when that happens, we see this strong subsurface cooling response, or basically shutting off the heat that could access that shelf originally from accessing it once this strong barrier is created. And that's what's shown here on the bottom left, the strong subsurface cooling anomalies. And I want to mention importantly that the wind stress plays an important role in setting the magnitude of either the subsurface warming in this region that we see in ESM4 or the magnitude of the subsurface cooling in the case of CM4. So again, wind stress acts as an important control on the isopycnal slope. So as you move the wind stress poleward, you actually shoal isopycnals. So it's working in the opposite direction that the meltwater would act to in the case of CM4. And this allows for, it's basically in CM4, these two forces are counteracting each other. And this reduces the subsurface cooling anomalies. The meltwater wants to shut off that region and lead to these downward plunging isopycnals, while the wind stress, the weakening of the easterlies as the wind shifts poleward, actually wants to shoal the isopycnals. So in the combined forcing experiment, ant-water stress, you actually have slightly weaker subsurface cooling anomalies because of that. And in ESM4, these forces actually work to reinforce each other. So in ESM4, you have this strong subsurface warming due to the decreased vertical transport of heat to the ocean surface as you put that freshwater cap on there. And the wind stress acts to bring more heat up offshore into those regions. So now you're trapping more heat. So the wind stress is important on the shelf, the response and controlling the magnitude of it. So just to go back through, so if we put the pieces together, what we found was basically a tale of two different feedbacks. So in general, in the control state and observations, the Antarctic shelf has this warm regime which runs along the West Antarctic shelf, and the rest of the shelf is generally a cooler regime or a cold shelf, and that is where you have this barrier of the slope current. Now, when we impose the wind stress and the meltwater forcings, we found that in ESM4, which is our half a degree model, which in its mean state had a very weak, not well-defined slope current, more meltwater is able to move off the shelf and become incorporated into the open ocean. So we did not see a very strong freshening on the shelf. And the warming along the shelf happens as a result of reduced upward vertical transport of heat from that increased stratification. And actually, when that happens, this is coupled with a depression of isopycnals towards the coast that directs more warm offshore water to the shelf and warms the subsurface. And again, the wind stress helps with bringing more of that circumpolar deep water up in the case of ESM4. And we do not see an establishment of a westward jet off the shelf. So in this case, ESM4 would imply a positive feedback whereby increased meltwater would lead to subsurface warming, which if we coupled to an interactive ice sheet model may lead to accelerated further melting. In CM4, in the case of our quarter degree model, we saw strong freshwater trapping by a strong and accelerating slope current as we impose this meltwater perturbation. And what that did is it led to a development of a westward flowing slope current along the West Antarctic shelf regime, which led to this strong subsurface cooling. So in the case of CM4, which had a well-defined slope current, this would imply a negative feedback whereby increased meltwater would lead to subsurface cooling, which may act to limit further melt, importantly in this region in which we're currently observing the most ice shelf melting in the West Antarctic shelf regime. So CM4 produced results that are consistent with results from fine resolution models that have been published, and ESM4 produced results that were generally consistent with the coarse resolution models and the mechanisms described in those studies for the subsurface warming. So the key point that I want you to take away from this is that models with sufficient horizontal resolution to resolve an Antarctic slope current appear to respond differently to meltwater perturbations compared to coarse resolution models that have a less well-defined slope current. Or in the case of many of the CMIP5 and CMIP6 models, these models may not have a slope current represented at all at 1 degree resolution. So it's really important to resolve this current to get a better understanding of this cross-shelf exchange and how these regions may respond to increased ice shelf melting. So in ESM4, we had a very weak, broad slope current at a 0.5 degree, and this led to strong subsurface shelf warming, again, would imply a positive feedback. In the case of CM4, where we had this very well-defined, strong slope current in the mean state, this led to strong subsurface shelf cooling, and again would imply a negative feedback. So it's really important here. I want to emphasize that we really need models at differing resolutions to do these same studies so that we can understand if these results are robust, because these would have big implications for understanding things like regional and future sea level rise, because we really need to constrain how this region is going to respond as the ice sheet continues to melt, and understand these feedbacks and how they work. So in that, I'll just thank all my funding agencies and collaborators, and again, emphasize that we found a lot of really neat things in the surface response as well to these forcings, and I didn't have time to go into them since I only focused on the shelf. But this is under revision in JGR Oceans, and I'd be happy to kind of share those results with anyone if you just contact me via email. So thank you.
Thank you, Rebecca. Questions for Rebecca? Bill Large.
Yes, thanks, Rebecca. I have a vague recollection of a talk many years ago, like 10, where someone suggested that this westward slope current went unstable with resolutions of around a couple of kilometers. And it was the instability and eddies thereof that achieved most of the cross shelf transportive properties. Do you include anything like that, or is there a prospect of parameterization as a function of resolution, so both your coarse and fine might actually get similar cross exchanges based on what a very high resolution model might get? Is that your recollection, or do you know about that?
Yeah, so eddies are very important in governing this cross-shelf exchange, and they act as a mechanism to oppose the steepening of the isopycnals that the meltwater induces. And that is an important thing to consider in our study. So CM4 has no mesoscale eddy parameterization employed in it. So the response that we're seeing might be overestimated in that sense, in that we don't, at the latitudes of the shelf, at the continental shelf, we're not resolving those processes. And even in the 10th of a degree Mormon et al. Study, they're also not going to be capturing a lot of those processes. But in ESM4, there is a mesoscale eddy parameterization employed. So that is one important thing about this study to keep in mind, because that does, as you mentioned, acts as a control on that. So I think it would be interesting to do a more detailed study where we take the same model configuration and employ eddy parameterization, and then not employ an eddy parameterization, and look at first how the slope current is represented, and then how does that control kind of the magnitude of this response. So yeah, that's a very important process to think about.
I think just to follow up, I was thinking the same. I think I was thinking of the work by Andrew Stewart and Andy Thompson on this process. I think maybe was what Bill was remembering. And you know, I was going to ask if you could clarify the distinction between the closures in the two models, and you just did. So
yeah, in the work by Stewart and Thompson, I believe they're using a 1/48 degree simulation with 1 year, so they're able to resolve, you know, those processes. But I think, yeah, so that's really important. But yeah, with climate, if we're interested in climate scale problems, I think we're very far away from having models where you can run fully coupled simulations at those resolutions. So I think there's a lot of work to be done to understand the role of those processes in governing the response.
Teresa has her hand up.
Yeah, following right onto that, what was the timescale of the response in your models? How long, you know, after you turned on the freshwater forcing did you see these things?
It's pretty rapid, like the sea ice response. So I didn't show that in here, but we have this rapid sea ice thickening and a cooling of the surface in response to the meltwater, specifically in the South Pacific. And that occurs within a matter of 10 years. And the acceleration kind of all the way around the slope, I would say, happens in 10 to 15 years, definitely less than 20 years. So it's a pretty rapid, generally a rapid response. And then it kind of like plateaus in each of these ensemble members.
Thanks. That's really interesting. It makes me think about what we might be able to see in our simulations with the much higher resolution in the Southern Ocean.
Yeah, and I think off of your work, the next thing that we thought about is, delivering fresh water at the surface, particularly in Antarctica, is not the most realistic setup, where most of the melting comes, at 400 meters or so at the base of the ice shelves. So actually it'd be interesting for us to talk more about maybe how to design those experiments.
Yeah, definitely. And I think the icebergs, I think, have interesting implications in Antarctica as well. So definitely talk more.
Yeah.
Okay, great. Okay, I think we need to move along. Next up, we have Ian.
Good.
Yeah, more or less. We see I don't know what you're using here, but we see a tab at the top, but there you go. Full screen. Okay, good.
All right. So this is ongoing work that we've talked about here before. Got a lot of people involved. Alistair, this is alphabetical order. So Alistair Edcroft, Scott Bachman, Fred Castruccio, Jessica Kenningson, Will Clabber, Phil Pigeon, and Zofia Stanley. I'd like to highlight Zofia Stanley. She was a graduate student working with me and has graduated. She graduated this summer and has moved on to NOAA Earth System Research Lab. And also to highlight Jessica Kenningson, who's a postdoc who's been working with me for about 1.5 years on this. Also, I'd like to thank and acknowledge Gustavo and Alper, who provided a lot of support. We couldn't have gotten this set up and run without them. So background, we're correcting an error in the computation of density. Density, of course, as we know, depends on temperature, salinity, and pressure. The pressure is usually hydrostatic in these models, so it's a function of depth only. And in a finite volume model, which most of these models are, the quantity that you want is averaged over a grid cell. And so if you want density, then you want density averaged over a grid cell. The problem is that the average there over a grid cell doesn't pass through the nonlinear equation of state. It doesn't commute the nonlinear equation of state. But the way that the model computes density on the grid is it takes cell average temperature and salinity and plugs them into the equation of state. So rho sub m here that I've got is what the model computes, and it's not exactly equal to what the model would like to have, rho bar. That difference, delta rho, is not trivial. It can be dynamically significant. So Jean-Michel Brancard, I think, was the first person to kind of notice this in the context of ocean modeling. And he developed a parameterization that corrects the computation of density. Now, density gets used everywhere in the model. There's lots of places where you need to use density in the model, and this correction that Brancard developed was only used in the buoyancy force, which is, of course, balanced by the vertical derivative of pressure. And so when you plug in this parameterization only in the buoyancy force, the only thing that you're changing about the model is basically the pressure gradient that shows up in the momentum equation. So Brancard ran it in 2-degree NEMO and found that it changed position of the Gulf Stream, North Atlantic Current. It's stochastic, so it also increased variability. So it's not trivial. It actually does something. It has been used for ensemble simulations, a data simulation within NEMO since then. It's implemented in some other models. ROMS has it, I believe, some version of ROMS. Fred Castruccio at NCAR was working on a POP2 implementation, and Alistair implemented this in MOM6, or he implemented something very similar in MOM6 and spoke about it at the 2018 fall meeting. And then in early 2019, Fred, Alistair, myself, and other people on the team just all got together and decided to join forces and work on it together. And our goal was to develop a new correction of the density that was more accurate than Brancard's, more computationally efficient than Brancard's, especially more Alistair noticed that his implementation in MOM6, which was very similar to Broncar's, was quite expensive. And then also we wanted to put this correction not just into the buoyancy force, but into other parts of the model that also rely on density. So we started out offline, used high resolution pop simulation, 1/10 of a degree, and did some coarsening, and then developed the parameterization offline. And that was reported in a James paper here that was published in 2020, led by Zofia. Our results, I'm just going to go through it fairly quickly. Our result was that our correction to the model's computation of density is here on the right. And it ends up being second derivative of the equation of state with respect to temperature multiplied by this stuff. And this stuff over here is a parameterization of subgrid scale temperature variance. And it ends up being the resolved temperature gradient multiplied by the grid size, quantity squared, times a constant, which is in principle tunable, but we estimated it offline to be about 0.2. This parameterization, the deterministic one, does not fit the data precisely. There is some spread in our offline analysis, and so we developed a stochastic parameterization to model that spread. And it's quite simple. You end up just multiplying the deterministic version by e to the chi, where chi is Gaussian. So you're just multiplying it by log normal noise. That noise that we're using is uncorrelated in space. It's white noise in space. It's not white in time, though. It has a decorrelation in time. It's red noise. And the decorrelation time depends on the resolved flow. So it varies from, say, 3 days to 180 days. If you have high resolved kinetic energy, so the core of the Gulf Stream or something like that, then you have a quick decorrelation time. And if you have low kinetic energy, then you have a long decorrelation time. And that was all developed not based on theoretical ideas, but just based on comparing this to the high resolution data that we coarsened. So our model is a better fit to data than Broncar's. Now, Broncar did not fit his model to data, his parameterization to data. And so it's maybe not a fair comparison, but ours is a better fit. It's a pretty good fit, as we report in that paper that I mentioned. It's also a lot cheaper. So we've, I think, succeeded in those first two goals that we set, although there is, certainly work to be done and improvements to be made there. But we then moved on and actually implemented this thing in MOM6. So we put it in the pressure gradient force computation. So we put it in the buoyancy force, which then you use to compute the hydrostatic pressure, which goes into the pressure gradient that appears in the momentum equation. Alistair mainly did that, so thank you to Alistair. We also implemented it in the computation of the isopycnal slopes, which are used in a lot of places, in particular in the GM-ready parameterization. And then we also put it in the mixed layer eddy mixed layer restratification parameterization. That parameterization also relies on a density gradient, so we correct the density there. And those latter two were implemented largely by Jessica Kenigson. And I should say that Phil Pejon was instrumental in helping us get the stochastic part of this going. So we've run all the tests for all three of these different cases. They're all complete, but they're not all fully analyzed. We had some trouble with bugs and logic in the second and third ones. So I'm only going to report results for this parameterization being implemented in the computation of the pressure gradient force in this talk. So our configuration is global MOM6 2/3 of a degree. It's the workhorse NCAR configuration. Z star vertical, 63 layers. It's a G case, so we do have active ice. It's forced by JRA 55 reanalysis winds. So we started everything from a previous spin up that had been run by Gustavo, I think, for the full JRA cycle. So it was already spun up. And then on top of that, we ran a whole new cycle. And I'm going to report results today that are basically averaged over the last 50 years of that long run. The cost is pretty low. When you do this with the deterministic version of the parameterization, it adds about 1% to the runtime. And when you do it with the stochastic version, it adds about 2%. Before I tell you what we saw, I think it's interesting to step back and say, well, what would we expect? So the correction to density is a product of two things. So we have this second derivative of the equation of state multiplied by basically the gradient squared. The second derivative of the equation of state is basically a constant. So that's not varying much spatially. So most of the spatial variation in terms of where is this thing going to be active depends just on the resolved temperature gradient. So if you have a big resolved temperature gradient, you expect to see a relatively large correction to the density there. Now, if you have a big temperature gradient, you are going to have a big density gradient as well, unless that temperature gradient is compensated by a salinity gradient. So if you have warm, salty on one side and cold, fresh on the other, you have a compensated front. And in that case, because this correction only depends on the temperature gradient, you'll get a big correction of density sitting on top of a density front that's maybe not as big as it would otherwise be if it wasn't compensated. So those are places where we expect this thing to be sort of more dynamically relevant. These kinds of fronts occur everywhere, of course. I mean, they're in the Southern Ocean, Gulf Stream, Kuroshio, etc. So that tells us where we expect this thing to be active. And then when it is active, what do we expect it to be doing? So we're only changing pressure. We're changing pressure gradients. This is a low-res model, so most of the dynamics that are in here are balanced, geostrophically balanced. And so when you change the pressure gradient, you're going to be changing the geostrophic circulation. So the effect that we expect to see is in regions with strong compensated temperature fronts, we expect this to change the current structure. All right. So here we have a plot of the magnitude of the density correction itself, averaged over the last 50 years, and it's just at the surface. These corrections are actually typically biggest at the surface. Lateral temperature gradients are also typically biggest at the surface, which explains it. And they are where we expected them to be. So they're on Gulf Stream, on Kuroshio. You've also got these things happening sort of in the Southern Ocean, South Atlantic Current, south of Africa here. There's also something happening off of New Zealand here, but you don't see it because it gets cut by this projection. So that's where this thing is active. Not really active on the equator. Don't really expect to see any changes on the equator. Also not really active in the Arctic. You can't really see that on this projection either, but there's really just not much going on in the Arctic. So that's where it happens. Now, what does it do? So here I'm showing the difference between the control run without the parameterization and the run with the stochastic parameterization. It's experiment minus control. And then I'm showing temperature on the left, salinity on the right. These are both 50-year averages. And say, it's at 400 meters depth. So the biggest change is in the North Atlantic. You do see changes elsewhere. So you do see changes, for example, in the Southern Ocean there or in the South Atlantic. And then there's a little bit of changes going on in the North Pacific and a little bit in the South Pacific. But the biggest change is clearly here in the North Atlantic, including the subpolar North Atlantic. So what I'm going to do next is go through some changes here, not all of them, but just go through a few of them. I'm going to start at the South Atlantic and work my way north. So here I'm showing, again, the anomaly, the difference between the run with the stochastic parameterization and the run without. And I'm showing potential temperature. And I believe this plot is at the surface now. We're not at 400 meters depth anymore. These are seasonal averages. And so here, JFM, Southern Hemisphere, we're in the summer. And you can see there's a bit of an anomaly there. What's happening is the Brazil current comes down. That's warm and salty from the north. And you have the Malvinas current coming up from the Southern Ocean. That's cold and fresh, relatively speaking. They meet at the Brazil-Malvinas confluence, and there, right there, you get a strong compensated temperature front. So you expect our parameterization to do something strong right there. And it does, and it shifts the current. It shifts it slightly equatorward. And so as a result of that, you have the Brazil-Malvinas current coming down. It shifts a little bit. I'm sorry, I said equatorward, I meant poleward. It goes a little bit further south before it separates. And that's why you see this positive anomaly. You also see the same thing in salinity, which I'm not showing, but you see a warm anomaly there because the current has gone a little bit further south. And you see a cool anomaly here because it has not, it used to be separating here and bringing this warm, salty water in, and now it's separating just a little bit further south. So you see a cold anomaly there. And then as the seasons progress, you see this anomaly that happened in the summer propagating out into the South Atlantic along the path of the South Atlantic current. So it propagates, and then kind of dissipates here. There are changes happening locally. The parameterization is also doing something locally, which tends to shift the current slightly southwards, polewards. But the seasonal character suggests that it's driven by seasonality in the strength of this compensated front at the Brazil-Malvinas confluence. There's a few other things I want to talk about, so I'm going to move on next just to North Atlantic here. And here we have sea surface height in the North Atlantic, control mean on the left, and then deterministic and stochastic anomalies on the right. And you see a big negative anomaly here, and it's not really subpolar, subtropical, because you can see up here in the subpolar North Atlantic Erminger type C, you have a positive anomaly. So it's not that the subpolar gyre is going down and the subtropical is going up. Also, the boundary between blue and red is not really along the boundary between the gyres either. In fact, this blue anomaly appears to be sort of along the path of the Gulf Stream. So we have sort of a negative, a reduction in sea surface height along the path, which is not necessarily associated with shifting or strengthening. If the difference between blue and red were along the path of the Gulf Stream, then you would expect this to be associated with a change in the strength, but it's really not along the path. Let me look at the Gulf Stream path here. So the dashed line is the north wall of the Gulf Stream from a reanalysis product, EN4. So that's the 12-degree isotherm at 400 meters. The colored lines are the model results. The red one is the control. So you see the typical overshoot from a low-res model. And then the yellow and orange lines are the model, the experiments with the parameterization. So we do see that we're shifting the Gulf Stream a little bit south. We're not correcting the overshoot. We're making a little bit better. Underneath, the color that you see is actually the temperature anomaly. So the temperature has gone down. It's decreased here under the Gulf Stream, sort of. And if I go back to the global figure here, you can see that there's a negative anomaly of temperature at depth along the path of the Gulf Stream. We're not sure what's causing that negative anomaly, possibly a strengthening of the subpolar gyre. But in any case, we think that possibly this change in sea surface height is just a steric effect from having basically more cold water here and more warm water here is changing the sea surface height a little bit. It's only a couple of centimeters. It's not a big change. All right, once again, moving on, moving further north, we have Lab Sea and Nordic seas. And now what I'm going to show you is at the surface in winter. So top row is potential temperature, bottom row is salinity. And then on the right, we have the anomalies for deterministic and stochastic. And you can see that the subpolar gyre basically here, the Lab Sea and the Erminger Sea, they're both getting warmer and saltier. And then in the Nordic seas, you have, they're both getting colder and fresher. It's not quite as uniform in the Nordic Sea as it is in the subpolar gyre, but it is generally speaking getting colder and fresher. Associated with those changes are changes in mixed layer depth and ice thickness. So the mixed layers get deeper in the Lab Sea, in winter in the runs with the parameterization on. And then the sea ice is not as thick. You see a loss of sea ice in the lab sea. You see a corresponding gain of sea ice, though, here upstream of Denmark Strait in both of the parameterized runs. And that's consistent with the hydrographic changes. If you make the lab sea warmer and saltier in winter, you're going to get increased convection and it will go deeper. So that makes sense for increasing mixed layer depths. And then also, if you have warmer and saltier water near the surface in the lab sea, you expect less sea ice. Similarly, in the Nordic Sea, it's colder and fresher near the surface, so we expect less meltings, maybe a little bit more sea ice there. The question is, well, where do these come from? Where do these changes come from? Couldn't really answer it for the path of the Gulf Stream, but I think we have a pretty credible answer here. So I'll go into that next. I want to talk about the current structure here as a background for explanation. So along the coast of Greenland, east coast of Greenland, you have the East Greenland Current coming down out of the Arctic with cold, fresh water passing through Denmark Strait, and eventually, goes around and makes it into the lab sea. Also through Denmark Strait, you have what I believe is called the East Icelandic Erminger Current coming up northwards and bringing relatively warm, salty water into the Nordic seas out of the Atlantic at the surface. So exchange happening in both directions across that strait. Here's a section across Denmark Strait, and I'm showing just the control experiment velocity. So this big blue is East Greenland Current coming down, and then this red bulge is the East Icelandic Erminger Current, I believe it's called, moving water north. Now, what the parameterization does, like I said, it changes density, it changes pressure gradient, and it's therefore going to change the geostrophic current structure. And it so happens that in this particular strait, the change to the current structure is to basically decelerate the flow in both directions. And it does this year round. The strength of the control current structure kind of fluctuates seasonally, though. So what you see is that in some seasons, this is a relatively large correction, and in other seasons, it's not a very big correction. Here I've got, again, surface properties. It's just potential temperature at the surface, anomalies, stochastic minus control. And you see here across the strait, you see a dipole forming where the flow has been reduced in both directions, which then causes you to have more warm, salty water on the southern side and more cold, fresh water on the northern side. And this is happening in boreal summer here. And that's because the background flow is actually weakest in boreal summer. So this correction to the flow has the biggest effect in summer. And then in the other seasons, the correction is not as strong relative to the mean flow, but this anomaly that formed in the summer then gets swept in both directions, sort of downstream. So you have the warm, salty anomaly going down the East Greenland Current and then into the Labrador. And then in the other direction, you have the cold, fresh anomaly. And the key thing is that in winter, that anomaly that formed in the summer makes it down into the Labrador Sea. And that's what causes the increased temperature, salinity, and then the associated loss of sea ice and the increase in mixed layer depths there. So we're glad to have an explanation for that, even if we can't explain all of the effects that this parameterization is causing. I'm not entirely sure where I am on time. Yeah. So here's my summary. I'll just leave it there. Did you say I was done?
Yeah, we're at 20 minutes.
Okay, I'll stop.
Okay, thanks. Gökhan.
Yeah, I think as you may have also said it at the beginning, a motivation for implementation of this parameterization is to try to reduce biases, particularly in the North Atlantic, of the control simulation. And in your presentation, as far as I can tell, you showed only differences between the parameterization and the control. And if you look at the surface temperature and salinity differences, they are at most of the order of 0.4, 5 degrees C, even smaller in temperature, and only 0.1-ish sort of in surface salinity. And those reduction, and I cannot tell whether actually they are improving or making it worse, the biases in the simulations. So if you actually plot the differences with respect to the observations, have you done that, I guess? And the change in sort of the bias reduction or increase would be relatively marginal. Would you be able to comment on that?
Sure, yeah. So I would say our goal actually in implementing this is not to correct a bias in the output of the model. It is to correct a bias in one of the computations that happens within the model, the computation of cell average density. And I think that we have legitimately done that. The downstream, sort of the integrated effects of that correction may not necessarily have a big impact on the biases compared to observations. They may improve, they may make things worse, but then we know that these models are sort of a Rube Goldberg of contradicting errors, right? Compensating errors. So we weren't trying to reduce the bias. We were trying to improve this specific component of the model. Another thing is the temperature changes are not that big. I guess this is, yeah. So the temperature changes, half a degree maybe, max salinity, half a PSU. But then the changes in mixed layer depth are actually fairly significant. We have, up to 100 or so meters of mixed layer depth changes. And then sea ice, I think, is also, the sea ice changes are not super big. But I mean, what we were doing here is really looking at sensitivity of the model to what happens when you put this parameterization in, what happens when you correct this specific problem that's happening in the model, not necessarily try to make the model closer to observations. That's more of a tuning exercise that involves trying to deal with all the compensating errors from all the different parameterizations. I think I'll stop there. I don't know if that fully answers the question.
Yeah, that's fine. Thank you.
Okay, we're running a little bit late. I see 3 folks with their hands up. If you have a very quick question, either Steve, Bob, or Mehmet, go ahead and ask now, or we'll have time at the end of the day to revisit things. Any of you?
I got a small one. Delta rho is positive in your simulation, in your presentation. In the Brancard, it's negative. Is it just because how you define it?
No, it's negative in this one as well. It's just that what I've plotted here is minus the correction because we wanted to put it on a log scale, and you can't do negative logs. Right?
Okay. Yeah.
So it is negative everywhere, as it should be.
Okay.
Yeah.
Okay. Thanks. And again, others had questions. We can come back to them later today. So for the last talk of the morning, we have Deepak Cherian from NCAR.
Thanks, Frank. Can you see my slides?
You're good.
Great. So yeah, thanks for giving me the opportunity to speak. My name is Deepak Cherian. I'm a project scientist in NCAR's Ocean section, and this is some work. I presented a kind of idea type or framework type version of this talk last year. So this is kind of a brief update. And it's still very work in progress. So I'm really open to suggestions on things that could be done with this new data set that I'll show. I have many co-authors. As you see, there are many pieces. So there's Emily Schroyer, Jonathan Nash at OSU, Oregon State, Aurelie Moulin, who's a postdoc at the University of Washington, Sarah Perkey at Scripps, and also a little bit of work from Yiming Guo, who's at North Carolina State University, and Frank. I've been chatting with Frank too. This work is funded by NASA's Physical Oceanography program. And so the work that I'm trying to do here is to go from measurements of turbulence to a long isopycnal eddy stirring that would usually be represented in a closed climate world by a ready diffusivity. And then at kind of a higher level, I've been trying to think of this as, how do we use turbulence measurements to really validate a model and try to go closer to what the raw measurement is. And so the framework that I've been thinking about is general temperature variance, so like T prime squared, and the pathways of temperature variance. And so the kind of fundamental physics is that when you're measuring turbulence at the very tiny scales, you're saying that variance is dissipated at the molecular scale at a rate called chi. And so if you're dissipating a bunch of variance, where is that coming from? And the idea is then, well, there's some kind of stirring process that is stirring a bunch of gradient and sending it down to smaller scales. You could also have sources of variance at the surface, but I'm going to ignore that. So we're kind of thinking, we're in the middle of the ocean, middle of the water column away from the surface and any kind of crazy source of variance. And then, so there's this idea, I think Chris Garrett maybe is the source, but there've been a few papers on it. So Garrett 1992, where you take a triple decomposition of a field. So T here is the total temperature. And we're going to split it up into three components, a mean component, a mesoscale, and a turbulence. The definitions for these are pretty heuristic and kind of very general. So you see that there's a lot of heuristic arguments here. And so the mean, think of that as like a basin scale temperature gradient. So it orders thousands of kilometers. It's a mean over multiple years, something like Argo climatology across the basin, right? So that very smooth field is the mean. And then the mesoscale we define as something like order 100 kilometers swirling things, timescales of order months. And then turbulence is going to be something like a breaking internal wave and smaller. So some in the vertical about 10 meter scales. And something like order of minutes or whatever n is the frequency, buoyancy frequency. And so you could schematically represent the vertical profiles as something like this. You have kind of a very large scale vertical gradient of temperature, a bunch of mesoscale eddy stirring that creates these wiggles. And then you have the turbulence, which is really small wiggles superposed on top of these two. And so the idea is that you have this large mean gradient. The mesoscale eddy field kind of stirs it around, generates a lot of lateral gradients. Somehow all of that gradient or that variance flows down to the microscale where you have these tiny eddies that stir them even more till your gradients become so large that molecular diffusivity ends up killing it, and that's chi. And if you've split up into a mean plus a mesoscale and then turbulence, you can think of the turbulence acting separately on the mesoscale, so these wiggles, versus the very large scale gradient. And so there's an implicit assumption of scale separation between each of these three components, which may or may not be well justified, but you kind of do that so you can make analytical progress. For like a concrete example of what this looks like, here's one profile. It's from the North Atlantic. I'll show you that it's from in 2 slides. But for now, the point is on the left, in blue is a vertical profile of temperature that I've kind of smoothed a bunch. In gray is salinity. And so you can see there's this kind of largish, and you're looking at the y-axis is pressure. You're going from 800 decibars to 1,300. So that's 500 meters of the water column roughly. You can kind of see there's a big gradient at this very large scale. At an intermediate scale here, I'm trying to show you the mesoscale stirring in terms of n squared and the contribution to n squared from temperature in blue and from salinity in gray again. If you look at this part of the water column, you'll see compensating temperature and salinity gradients, right? And they add up to give you the n squared, which doesn't really change by much. So that's a sign of mesoscale eddy stirring along an isopycnal. You're generating compensated TS variability. And it's something like 20 to 30 meter scales in the vertical. And then on the right-hand side, the last panel here is, again, n squared, and t squared, and ns squared, but now I've calculated it with 0.5 meter resolution temperature data. So you can see it's really spiky, and there are a lot of large values. I've sorted the field so that the n squared is always positive, but if I didn't do that, you would see a bunch of negative inversions too. And so you've basically captured turbulence as the profiler went down through the water column. And so this is real data showing you that large scale gradient, something like the mesoscale stirring signal in the n squared field, and then the pretty small scale variability superposed on top of that. And so the idea is that this, the amount of variance that the mesoscale pulls out of the mean field to generate this kind of variability eventually cascades down to the microscale where it's eventually dissipated chi. And if you have a climate model that's too coarse to represent mesoscale variability or that production term, then you have to parameterize it. And that's usually done using a ready diffusivity. And so the idea is, how do we use these microscale measurements when you're sitting here to tell us something about this variance pathway, because that's the one that's being parameterized and it's kind of hard to constrain. So like I said, there are I'm assuming that there are roughly two pathways. And I'm going to try and show you estimates of how much variance is falling to those two pathways from two different perspectives. The first is the mesoscale variance budget. And so first, I'll show you some values that are directly estimated for a POP 110-degree simulation that explicitly resolves mesoscale eddies. And so we can kind of calculate what these terms are. Yiming Guo, who's a graduate student, did that. So I'm very thankful for him for sharing his output. And so you can calculate this term, so how much is the mesoscale stirring the mean field? And then you can also calculate how much of that variance is being dissipated in some sense. And then finally, I will also look at the microscale variance budget. So you're sitting at this part of the phone. And I'm going to use data from this paper by Ferrari and Polzin, 2005. And you kind of talk about this part of the cascade. And we can assume that the residual at the microscale is going to represent the transfer from mesoscale to microscale. And so that's the commonality between these two versions, or these two budgets, is this scale transformation term, or how much is the mesoscale sending to the microscale. So if you're sitting in the microscale, you should be able to see it come in. If you're sitting at the mesoscale, you should be able to see it go out. And one's a model, one's data, hopefully they look similar. The reason this project got funded is because there's this cool new data set that is still being cleaned up, but basically they're stuck turbulence sensors. So here is a CTD rosette. Here are 1, 2, and 3 fast temperature sensors on the rosette. And basically every US ghost ship cruise since 2015 has had these things on there. And so there are a bunch of sections. This is not even the most updated figure, there's even more. And so we have basin scale Kaya measurements. And I've been thinking that this is a great way to use that data set, is to try and get to these quantities and try to talk about variance pathways for the basin. And so in the meantime, while the data set gets cleaned up, I've been looking at the NATRI experiment, which is the one of 2 times that people have actually tried this. And so thanks to the NSF microstructure database and Amy Waterhouse, as well as the cruise PIs, the NATRI data set is public. And so I've been looking at that a bunch. So we are in the Northeast Atlantic, so that's Spain up there, that's the Mediterranean. The NATRI experiment was a bunch of 100 costs in this little region, where there's a lot of TNS variability along isopycnals thanks to the Mediterranean outflow, and there's a bunch of stirring. Luckily, there is a ghost ship section that had a bunch of Chi data 20 years later that cut through this, so I thought this could be a good comparison. Okay. And so we've been thinking about variance pathways. And so I put my little schematic here on the left, which is originally from Chris Garrett. And on the right here is the mesoscale variance budget. And this is, again, all these terms were calculated by Yiming Guo. And he was very nice enough to share it. And so what I've done was take his output and then average it over that NATRI box. So on the right-hand side, over here, you see a red profile. So that's the horizontal stirring term. The blue is the vertical stirring term defined there. So W prime theta prime averaged times the vertical gradient. You'll see that at the top of the water column, the two of them match pretty closely. Somewhere in the middle between 800 and 1500 meters, there's a big gap. And then they come back together again. And so the difference is basically very closely explained by this purple curve, which is the dissipation term, or the amount of variance that is going from the microscale down to dissipation. In this case, it turns out that because the model is too coarse to represent the cascade down to the microscale, what ends up happening is the mesoscale stirring ends up building a bunch of lateral gradients, which then gets killed by biharmonic lateral mixing. So you kind of short circuit this variance pathway and just takes it out directly. And so the physical interpretation of this budget is that at the top, the blue and red agree. So that's basically a Jen McWilliams type thing, where you have eddy potential energy. So little bumps in the density field get flattened out adiabatically. And you're moving eddy potential to eddy kinetic energy, and then it goes down a whole energy pathway. And so I've kind of schematically put that up here as a kind of blue line that's moving away. And then so that's in the upper half of the water column. And so that's where you tend to have T surfaces and rho surfaces are basically parallel to each other. So rho is basically a function of T, so there's low spiciness. And that kind of dynamics is parameterized using the Jen McWilliams thing. Down here, where you see much different balance, is where T surfaces are inclined with respect to rho surfaces. That means there's a compensating TNS gradient along isopycnals. And over there, what you don't have is this, and it's instead very cheap, energetically cheap to store and generate a lot of T and S gradients. And so that's a long isopycnal stirring and mixing, and that's usually modeled using a ready diffusivity. In this particular model, because it's 0.1 degree and resolves the mesoscale explicitly, what happens is the eddies stir and you generate really strong horizontal gradients that then gets killed by harmonic mixing. And so what should be the scale transformation term, but in the real ocean, you would send it down to the microscale, is instead here directly dissipated using this biharmonic scheme. So here's now, I've added a second panel. This is the microscale budget. I've literally just copied the steps from Ferrari and Polzin and used their data. In red is chi, so that's the total amount that is dissipated, like out here. In black is an estimate of this pathway, which is the mean to microscale variance pathway. So it's, if you have these really tiny eddies, how much do they stir this basin-wide mean? And so there's some details on how you do that, but they say you can do that. I think it's convincing. And what you do is you take all the data and then you average it in neutral density bins, roughly 100 meter spacing, all 100 profiles, and you get these two vertical profiles with these error bars. And again, you'll see in this middle 800 to 1300 meter portion of the water column, there is a gap between how much is dissipated and then how much is generated by stirring the mean. That gap we assume is this mesoscale to microscale pathway. So there's a residual there, and I'm going to compare that residual to what we see from the model. And when you do that, it looks amazingly good to me. So again, on the left is a mesoscale budget, on the right is the microscale budget. Things that are steppy and have error bars are observations. And the solid lines are from the model. So you can see we're comparing this purple line, which is the dissipation term from the 1/10 degree model, with the residual from the microstructure data, which is the steppy purple line. And you can see that they agree pretty well. Down here, there are some small disagreements up there, but I don't think that is too important. They're pretty close. And so I think this is pretty great. I think what this is saying is that the model is explicitly resolving eddies and it's getting the production term right, and it's sending the right amount of variance down to dissipation, which in the model ends up being a biharmonic lateral mixing, which is not very physical, but the amount of variance that is being dissipated through that matches really well with what we can tell from this one set of observations that we have, which is kind of cool. Like I said, in a much coarser model, this purple curve is basically parameterized to a bunch of parameterizations. There have been a couple of proposals building off observations and some theory. So I'm referring to parameterizations by Sylvia Cole et al. From 2015 using Argo and mixing length theory, and also this paper by Grosskamp. And so you can take their diffusivities, multiply it by the gradient of temperature that I pull from the Argo climatology, and construct a vertical profile for how much those parameterizations say is being dissipated in that part of the ocean. You can see that there's, these dashed lines are the parameterizations. They look kind of okay in the top 1,000-ish meters. And then for some reason that I don't understand, they're pretty off. So by, more than an order of magnitude at around 1,500 meters. So they're different from what the 1/10 does. They're different from this one small set of microstructure observation does. I'm not entirely sure, but we can discuss. But they do pretty well at, decently well at picking out the peak and like getting the general shape of structure in the water column. Things that I'm doing, like I said, this is very work in progress. We have more data from these Go ship sections, but it still needs a lot of cleanup. I just found that if I took out one profile that looks suspicious to me, my error bars dropped by a factor of 4. So there's still work to be done, but hopefully I'll have a second set of data that we can use to verify all this stuff that I was saying. The other thing I've been thinking about is what happens in much coarser resolution models. So here's a 1 degree pop simulation that was run by Keith Lindsay. And I spent just very little time just doing, it has monthly mean output. So I took the ready diffusivities, multiplied it by an estimate of the along isopycnal temperature gradient squared. So that gives you a measure of variance that is being dissipated by the ready diffusivity scheme. And then on the right here in purple again is the pop 1/10. And I'm comparing that to this pop 1 degree model from the first cycle to the last cycle. And you can kind of see it starts off pretty well at the top, but it's still kind of off near the bottom. By the end, it's dissipating too little variance at 1,000 meters, and then a lot more in the abyss. I haven't had time to really look into this, but my next step is to just look at the temperature gradient field and see if that really explains the differences. And then just to be clear, in this 1 degree model, you don't really even get this mean to mesoscale production because it can't get resolved eddies. So the ready diffusivity scheme basically short circuits this whole pathway. And so we would want this ready diffusivity scheme to take out the same amount of variance that would have actually flown, moved along that pathway in a more high resolution simulation. So that's the reason I think you can start to try and compare these things, and why I think this work could be useful is in trying to consistently interpret all of these simulations with respect to microstructure observations. So that's my last slide. So that's what I've been doing, is thinking about variance pathways, how you get at them from microstructure observations, how they're represented in kind of fine resolution, like 1/10 degree, and then how those are parameterized in much coarser models. I'm really happy to hear any feedback or any suggestions you have on things that could be done with this kind of inferred profile. Thanks.
Okay, great, Deepak. Questions for Deepak? A lot of, oh, there's one from Steve Griffiths.
Thanks for the talk. I found it very interesting. At the very beginning, you were talking about, if you go back and show your vertical profile of your buoyancy frequency squared and variance, yeah, this, and in the middle panel, you were arguing that there's large compensation between temperature and salinity that doesn't affect the n squared much. And so that's an argument for along isopycnal mixing. Am I correct with that?
Yeah, Story. Yeah.
So this is kind of an esoteric question that is something that you might be able to lend some insight into. The question about local referencing versus, potential density versus locally referenced potential density comes up in some small corner of the theory community that is dealing with thermodynamics and questions about what is neutral in the ocean. Are you able to determine, based on this data, how accurate, or how is the mixing really neutrally oriented, or is it just roughly oriented neutrally? Say if you did an n squared calculation based on potential density reference to some value of pressure versus a local referencing of n squared, how far would you be able to determine you need to be neutral? I'm not asking it very precisely, but maybe you understand what I'm asking.
I think I do, because I've tried to understand those papers, but I have failed. Yeah, I don't really have an answer. I think my arguments and all this are pretty heuristic.
But you assume when you're calculating n squared, you're doing a local referencing, right? You're doing it the way
n squared is from, neutral density.
Okay.
Yeah. The NT squared and NS squared are kind of funny. I'll have to go back and see what I did.
Okay. All right. Thanks.
Okay. Other questions or comments for Deepak? Peter.
So Deepak, if you go back to that slide with right near the end with the ready profile.
Ready profile. That one.
Yeah. So are you suggesting in there that the vertical profile we have for the ready coefficient could be improved, could be stronger near 1,000 meters and weaker in the deep ocean?
That's one possible place, but so there's two things, right? There's K ready, and then there's the actual gradient of temperature, which is kind of an evolving field. So maybe the vertical profile is right, and the temperature, the spice field is just wrong or very biased. And I'm not really sure how you would pull that apart, right? Because the spice field is responding to that vertical profile too. So.
Well, a related question. I mean, have you looked to see how different are the Cole and Grosskamp kappa profiles from the ready profile from the model?
A good question. I haven't tried that.
I mean, those diagnostic kappas look fairly decent when you look at the dissipation curves. So.
Yes. Yeah. That's a good suggestion. I will do that.
Okay. Oh, Bob Hallberg.
Yeah, I might have missed this and you might have covered it. You're looking at the averaged squared gradient. You square the gradient and then average it, which means that if you have a spectrum that you're only partially resolving with the model, you only pick up the part that you resolve. As you go to a finer resolution model, you're integrating over more of a spectrum. And so even if they were identical in the resolved part, your metric picks up an additional piece just from the added resolution from increasing resolution. Is there something subtle that you needed to do to kind of extend the spectrum to estimate what that missing piece would be and therefore make different model resolutions directly comparable, or I guess equivalently, observations which have the full spectrum equivalent to models which have a truncated spectrum?
Yeah, it's a good question. The way I've been thinking of it is that the ocean dissipates a bunch of variance in a given grid cell, say. And then if you're thinking about the ready term, the model is doing a k rho times some lateral gradient every time step. And so if this term was accumulated online, I would think that those two, the observations and then the model online, like properly accumulated diagnostics, should agree. Does that make sense?
Yeah, no, I think so. No, I'm just kind of thinking about
there isn't. Yeah.
It's not that it's the dissipation that's constrained by the turbulence. It's not the gradient squared independently or the diffusivity. Put differently, if we were to increase K-ready by a factor of 2, you would reduce the gradients.
Yeah.
And so there might be compensation.
Yeah.
And in the same way, the fact that the model has a truncated spectrum may be compensated by the fact that it has a K-ready that is much larger than you would use if you were resolving to much finer scales. In other words, whenever we increase the resolution of our models, we tend to reduce the magnitude of the quasi-lateral diffusivities. Is that
right?
Is that a way?
I think so, because that diffusivity is effectively trying to get that downscale transfer to scales that are not represented or truncated, as you're saying.
Okay, thanks.
Okay.
Yeah.
Any last questions for this morning? Okay, if not, we will adjourn for now and reconvene at 1300, 1 p.m. Mountain Time for 3 more talks this afternoon, more model development oriented presentations. And again, if people think of questions they'd like to ask to this morning's speakers, bring them back, and hopefully the speakers will be back for the discussion later. And a reminder from Elizabeth that we'll be back on the same link this afternoon. So you can either leave it running or come back later. Okay. So we'll see everybody back at 1 o'clock.
Willie, can you hear me?
Yeah.
Okay, everything's good?
Yeah. No,
okay. Yeah, I got like really scared that I was going to start talking and, you know, it would do bad things.
Yeah. No, you fixed the problem, Willie.
No, I have not. That's the thing. I have not fixed the problem. It just happens sometimes.
Really? Oh.
Yeah, I think it's when I use like all the different video chats, like, you know, Zoom, Google Meet, Teams, all like kind of at the same time. I think all the permissions start getting mixed up and something weird happens.
I think you have too many computers on, you're mining Bitcoin in the background, and that's what's happening.
Yeah, my non-fungible tokens are doing quite well. Thank you.
Cool.
All right. Thanks,
All
Willie.
right, see you later. Bye. Hey, Willie. You there? Ooh. Now I hear. Now I hear the disco thing. But I cannot hear you. By the way, I was going to tell you that you have the stuff from Yemi here. You want me to bring it home? No, just leave it here. All right. See you later, Willie.
Okay, welcome back, everybody. I'm going to give it another minute. We're missing about 40 people compared to this morning, so it looks like they're starting to roll in. Okay, I think we'll go ahead and get started. Thanks for coming back. So this afternoon we have three talks related to more technical aspects of the model, MOM6. And we're going to start off with Gustavo is going to tell us about some work that has been moving us towards doing fully coupled simulations with CESM and MOM6. So take it away, Gustavo.
Okay, so I'm going to talk about the groundwork for incorporating enthalpy fluxes in CSM. This work is in collaboration, has been done in collaboration with Mariana Bertestein, Alper Altuntas, Frank Bryan, Gökhan Danabuşoglu, Bill Large, Keith Lindsay, and Peter Lauritsen. And I will start by giving some background in terms of the net surface heat balance in the ocean. So we have QNet, which is the total, the sum of all the terms, which are composed of the radiative terms, so the short wave and long wave, plus the turbulent terms, latent and sensible, plus the term that comes from the sea ice from melting or freezing ice. And the last term is what I call QH2O. These are the enthalpy fluxes, which are also called advected heat fluxes in the literature, like in Griffiths et al. 2016. And these are the heat content of water crossing the ocean boundaries. An example of that is if water is adding into the ocean via, for example, river runoff or rain precipitation, it increases the ocean mass and therefore it increases the ocean heat content. Ocean model that uses the so-called virtual salt flux instead of the natural boundary conditions or real freshwater flux have a zero enthalpy fluxes. They don't have to add the enthalpy the fluxes. These models could have, but no, they normally not have those terms. And when a real freshwater flux is applied in the ocean model, the associated enthalpy fluxes have significant contribution to the net heat budget, and therefore their inclusion is critical for the integrity of long-term climate change simulations. Now let's look at a simplified way of computing these enthalpy fluxes that are coming from the mass transfer. So we have basically water is coming in three states: liquid, solid, or frozen, and vapor. So for example, frozen is the land ice model releases an iceberg which falls into the ocean, as shown on the top here. Liquid is rain, and vapor is evaporation. And I'm putting an asterisk in a footnote here that is a simplified way of computing. That's the following what is currently done in MOM6. And if one wants to be more rigorous, you can use more advanced energy equations that include enthalpy fluxes associated with mass transfer followed across all components. So like all components must agree on the temperature scale, on a reference temperature, specific and specific enthalpy as well. But it's beyond today's talk to go into the details of those more advanced ways of computing these energy equations. So I'm going to use a simplified way following what's currently done in MOM6. So in MOM6, we compute enthalpy flux per grid cell from adding and removing mass. I'm giving an example here, for example, from frozen runoff. So then QROFI is equal to the mass of the frozen runoff times SST times the seawater heat capacity. And we follow this equation for all the other terms. And then in the end, you have KH2O equal the contribution from liquid precipitation, frozen precipitation, evaporation, ice runoff, liquid runoff, and condensation. So all of these terms come at SST. So it's a mass times SST times seawater heat capacity. I'm using evaporation here, but MOM6 uses a content of the mass leaving the ocean. It's equivalent to evaporation. So if we go now and download CSM with MOM6 and run a fully coupled simulation out of the box, the enthalpy fluxes are not being accounted for by the other components, just within MOM6. And if you run this model for long enough, in this case, I've run for 20 years, you get an imbalance of approximately minus 0.25 watts per meter square in the system. So the way you do that, you look at that, you see that the coupler is reporting a global average over the entire period of the run of 0.26 watts per meter square. But then the heat content change in MOM6 between the beginning and the final of the simulation was 0.21 watts per meter square. And the difference, minus 0.25, is exactly what's missing from the fact that the coupler is not dealing with this enthalpy flux. It's just being dealt with within MOM6. So this difference between MOM6 and the coupler is negative because precipitation tends to occur over cooler SST regions than evaporation. And the above value, which includes not just P minus Z, the contribution from P minus Z, but also river runoff, frozen runoff, and etc., is consistent with the global mean of just from the heat from P minus Z, so the LPRAC and evaporation reported in the literature. So these are the two biggest terms, they dominate. So the value that I'm reporting is consistent with what has been previously reported in the literature. So to fix this issue in CSM, we propose two solutions. The first one is the ideal solution, but it will take a really long time to do that, in which all components must keep track of the enthalpy associated with the mass exchange across components. In that way, in addition to doing that, as I mentioned before, there must be some consistency in the way that the energy budget is treated within each component. This is a monumental task. It's going to take a lot of time for CSM to be at this stage. However, some components have already started working on this. So Peter Lauritsen is already thinking and working towards doing that in CAM, and we might hear from him on the upcoming working group meeting from the atmosphere group. And however, instead of waiting for all of the components to do that, we decided to follow a short-term ad hoc solution where we will compute the enthalpy terms relative to 0 degrees Celsius in the coupler, then add a so-called global fixer to the sensible heat that's sent to the atmosphere. And I'm writing down what this fixer, how this fixer looks like. So basically, we have the sensible heat that's sent to the atmosphere, and we will add this global fixer to this term, where we basically do we multiply the area times the QH2O for each grid cell, sum it up, and then divide it by the total area of the Earth. And we are following what other climate models have done. For example, E3SM, they have applied a similar global fixer to keep their heat balance as well. So I've shown before how MOM6 computes the enthalpy fluxes internally, but now we have decided to do this calculation in the coupler, in particular, just in UOPSI. We're not pursuing this with MCT. I'm pointing the module here on the top where these modifications have been added. And we also modify slightly the way the equations for each of the enthalpy terms. So for example, the liquid water contribution, so from liquid runoff, liquid precipitation, and also condensation, we use this formulation. So we take a max between SST and 0 times the mass times CP. So in other words, that everything that's liquid and is falling into the ocean cannot enter below 0 Celsius. For frozen water, such as ice runoff and frozen precipitation, we do the opposite. We take the mean of SST in 0. So everything that's frozen and falls into the ocean cannot come in above 0 degrees Celsius. And for the evaporation, we don't apply any limiter. We just use the SST. And by the way, these are, we're still kind of working on what's the best way for doing this, but these are the equations I've used for the results I'm going to show today. So since there were significant code changes that had to be done in MOM6 and as well in the coupler to do all this plumbing and provide the enthalpy fluxes via coupler, it's therefore useful to perform a global heat budget check consistency after I've done all these modifications. And this is something that, this kind of check is something that we start doing since we incorporated MOM6 into CSM, and we took the notebook that Steve Griffiths prepared a few years ago, and we've been using this often and often to do this type of checks. So basically what we do is we have the total surface heating, which is the area integral of Q net plus Q frazzle. So the Q net that I showed before just included the surface terms. It does not have frazzle in it. So if you want to account for all the heat fluxes in the ocean model, we need to add Q frazzle. And then we also have the seawater heat content between, let's say, 2 time steps. So the equation number 8, we use an average between the 2 time steps. And then equation number 9, we get 2 snapshots in the extreme of the bounds of where we did the average. And the seawater heat content change is given by CP divided by the time difference between the 2 snapshots. And then we have the vertical integrated potential temperature difference, which is then integrated in area. So for self-consistency, equation 8 and equation 9 should be equal with the interpolation error. I'm just pasting here a screenshot of the notebook when I ran these tests. And the last 2 rows here show the residual. The top residual is with respect to equation 8, and then the bottom residual is with respect to with the heat content. I think is the second time step. So the number is with interpolation error. It's balancing, and therefore we check this box. In addition to that, we also need to make sure that the net heat budget across all components is balanced. So I've run the model for 28 years, and CSM has the option to print out a table that shows all the terms, shows each column here is a component, and each row is one of the terms. And what we want to look at is the very bottom right value, which is 10 to the minus 3. It's acceptable given that the model has lags and so on. It's similar to what we get with POP. So we are happy with that. And we are now currently working with scientists from AMP to tune CAM and reduce the HEM sum imbalance, which is shown here at the bottom of the HEM column, which is equivalent to the rest OM value, which in this case is large. We want to reduce this from significantly before performing longer simulations. So now let's look at some of the plots from simulations with this new method where the enthalpy flux is computed via the coupler, compared in relation to a simulation where the fluxes are computed internally in MOM6. I refer to that second simulation as MOM6, and the first one as CPL. So we are looking at QNet plus QFrazzle. So this is the total amount of heat imposed into the ocean, average over 28 years. The mean for the CPL run is 0.79 watts per meter squared. And if you do a difference between CPL and control, the mean is 0.07. So when we add this new formulation for computing enthalpy fluxes, the P minus Z, well, no, the heat associated with the mass being added is slightly larger than the way MOM6 was doing before. And this leads to overall increase in the global mean ocean potential temperature as shown in this bottom plot. If you now look at only the enthalpy fluxes, all of them combined, again, the left panel is using the new method, and the right panel is the difference between the two. We see that the difference is negative, meaning that that's what I just said, the minus 0.27 in the new method is adding more heat into the ocean just because of the formulation we are using, and this will become more clear in this panel. So now I break QH2 by all the components. The first column is the new run, CPL. Then we have the MOM6 way of doing it in the second column, and then the third column is the difference between the two. Overall, we get a slightly, the ocean is losing more heat when we do the CPL method versus the MOM6 method. And the only major difference between the two is with the frozen precipitation, which is one is negative, the other one is positive. And that's because we're applying that minimum constraint in the new formulation. Other than that, the other terms are pretty comparable. And again, the biggest terms are the liquid those coming from liquid precipitation and evaporation. They dominate. So summary and next steps, CSM and its components, with the exception of the sea ice model, which works in terms of enthalpy, so it's been doing that from the beginning, having been built based on an ocean model that uses virtual salt fluxes, and therefore enthalpy fluxes across components have not been accounted for up to now. And by not accounting for these fluxes, there is a net heat imbalance in fully coupled simulations, which is large, and it is unacceptable for doing long-term climate change simulations with CSM MOM6. To fix that, we apply this fixer, this short-term fixer, where we compute the enthalpy terms relative to 0 degrees Celsius in the coupler. Then we add a global fixer to the atmosphere sensible heat. We perform global ocean heat budget consistency check, and we also verify that the net heat budget across all components is acceptable. And as a next step, we are tuning CAM to reduce the imbalance, the rest OM, before performing long simulations. And I'm happy to take any questions.
Okay, thanks, Gustavo. Steve Griffiths.
Thanks, Gustavo. Great work. A couple of detailed questions. The fixer, is that applied every time step? And the heat capacity, is that freshwater heat capacity or seawater heat capacity?
The fixer is applied every coupling time step, ocean coupling time step. And we're using the seawater heat capacity at the moment.
So does it make sense to use the seawater heat capacity with the fresh water coming in and out? I mean, it's at the level that you're talking about, it's going to make some difference, not a huge difference, but you might just consider that.
Yeah, so as I said, I think if we have a unified framework in terms of the energy equation across all the components, once we do that, I think it will become clear which type of heat capacity we should be using. And I've just started looking at the literature on that. The weather people are doing this already, and we're kind of falling behind in the climate. So now Peter Lauritsen is taking the lead here, NCAR, and we'll have to be very careful when we come up with this long-term solution.
Thanks.
Thank you.
Bob?
So one comment first. If we interpret our potential temperature as conservative temperature, as Trevor McDougall would advise, then by definition, we have a single constant heat capacity. Basically, it becomes a rescaled enthalpy variable. And then the equation of state is written to take into account the differences between the in situ temperature or potential temperature and this conservative temperature. And so I think that this all holds together in a really nice way. I had one question though. You have a floor of 0 degrees on the enthalpy of liquid water coming into the ocean, which seems appropriate for precipitation. But if any of that liquid water is actually melt at the base of the sea ice, that enters the ocean not at 0 degrees Celsius, but at the freezing point of seawater in some little molecular skin layer, which can be quite a bit below 0 degrees Celsius. It's close to the freezing point of seawater. This is about 8 or 10 slides back where you had this minimum. Is that in there? Whoops. There you go. So the enthalpy from liquid water, are you providing liquid water from the sea ice to the ocean? In which case that max with 0, there should be something different done under sea ice.
So I didn't mention, like up to now, within MOM6, so the sea ice give us a mass flux, and it also give us a heat flux. And that heat flux that the sea ice give us, I presented on the first equation, includes the enthalpy in it as well. So we don't need to double count here. And so I'll have to remove, I have a big pull request coming in which I will remove the enthalpy contribution by melting ice.
Okay.
Is already
okay. So this is
yeah.
So these are only if you need to come up with a definition from enthalpy for fluxes from a component that isn't taking care of that.
That's correct. Yeah.
Cool. Thank you.
Thank you.
Okay. Any last questions for Gustavo? Okay, thanks. Well, this was down in the weeds technical stuff, but it was absolutely critical for us to begin starting to do coupled simulations, and we're now on that path. So it's great work. Okay, next up is Scott Bachman, who's going to talk about alternative vertical grids.
Cool. Is my audio good?
Good.
Nice. Okay, and can you all see this?
Yep, it's full screen. Good.
Okay, great. All right. Well, thanks Frank and Ian for letting me talk today. And before I start, of course, acknowledge my primary co-conspirators, Andrew Gustavo, Shane, and Jeffrey Early, whose work over the last couple of years sort of inspired this work. All right, so before I talk about this new grid, let me give you some background. So we have sort of a default set of grids we like to use in large-scale ocean modeling, most of which you're all probably familiar with. Got geopotential or Z-star grids, which is used in MIT GCM and of course other models, which is good up near the surface mainly. It gives control, it gives you really good control over how your grid resolution varies with depth. You've got your isopignal grids, which is used in gold, which is nice because it's generally aligned with the flow in the ocean interior. And so it keeps some measures of spurious mixing to a minimum there. You have your sigma or terrain following coordinate, which is used in ROMs, which is really nice for representing bottom flows. And we also have essentially what we call hybrid vertical grids, which combine one or more of the above. So for example, you have Z-star grid near the surface, tapering into an isopignal grid in the interior, which of course is meant to combine the strengths of those and to minimize weaknesses. Now, of course, each of these grids, as I suggested, has their advantages and disadvantages. Some general challenges when we talk about these grids is that, well, one, you have spurious mixing from truncation errors in your vection schemes, that's not specific to any one of these grids. It's just sort of a general problem with using discretized equations, but it can be worse or better depending on which grid you choose and which direction you're thinking about. For Eulerian grids like those above, you have a CFL condition, of course, always in the horizontal direction. For the vertical Eulerian grids, the CFL is generally most restrictive in the vertical direction, which we'll talk about in the context of Ale in the next slide. And then we have our well-known pressure gradient errors when you have adjacent layers with different thicknesses or depths. So sort of the cousin to this problem is the one that's kind of notorious to ROMs, which you have a sigma coordinate and you have a topographic slope. The equation for the bottom pressure gradient is given in that box there, which appears as the difference of two terms. And the term on the right is a partial d partial x, which is essentially the bottom slope. It means that that pressure gradient can be really sensitive to the value or the representation of that slope, and it can create spurious geostrophic currents and all sorts of other bad things. So now, we have in MOM6, we have this Ale algorithm, or arbitrary Lagrangian Eulerian. Note that Ale is not a grid, it's actually an algorithm or a procedure of steps with which to step forward the model. The nice thing about Ale is it enables you to use general coordinate models, right? So you're essentially obeying the equations without having to necessarily define them in terms of depth or density or whatever. So the thing that makes MOM6 special is that we're using the purely Lagrangian form of Ale for the vertical grid, in which we are not letting any cross-coordinate transport, or well, not any cross-coordinate advective transport occur. So the grid moves as if your effective W is 0. And that's, of course, followed by a remap step. So a really nice way to conceive of this is in this figure from Steve's paper 2 years ago. So thanks, Steve. So let's say you have an initial state there on the left with a nice grid, or nicely laid out, and you have some state variable that's indicated by the colors. So dynamics will take over. It'll move the grid around. So that's essentially the Lagrangian vertical coordinate. It deforms the grid somewhat. And then, so rather than using this deformed grid, we want to actually come back to the initial nice grid during the next step. So we move the grid back from its deformed shape back to its initial sort of flat configuration here in the middle. And then we remap all the state variables from the deformed state back to how they would look on the initial grid. And then the final state over there on the right, you're now back on the initial grid, but your variables sort of reflect what happened in that Lagrangian step. Sorry, spam. So the question is, we have this regrid remap thing, which is sort of crucial to Ale. Can we do something interesting with the regrid part? So that's sort of the overarching question here. And so the philosophical question I like to pose sort of to motivate this is, what is the goal of modeling and what role does the grid play? So, I mean, there's a million possible answers you could give to that, but the one I'll pose here is that we want an exact solution to our governing system of PDEs, which I'll call F exact. But when we're using a discretized model, we get a solution to an approximated system of PDEs, which is F approx. And then, so you could say the goal is, of course, to minimize the difference between those two things. So what role does the grid play in that? Well, consider this thought experiment. So let's say we had a vertical column, and that column had some baroclinic modes in it with this hypothetical structure I'm showing here. But I didn't tell you what that structure was. You have no knowledge of it. So let's say you have 20 points. I'll give you 20 points to distribute throughout this column to get this modal structure, which you don't know, as best as possible. So without any a priori knowledge, you'd probably say, okay, well, let's space them out evenly and hopefully we'll get lucky, right? So in this particular case, it worked out okay. So, if you space those points evenly, get, for the most part, the turning points and the zero crossings of those modes. So, okay, that's fine. But of course, ocean models have this troubling tendency to evolve. And so sometime later, that modal structure changed and it starts looking like this. Again, you have no knowledge of it. So what happens if you use that evenly spaced grid now? Well, that's not good. You know, now it didn't do a very good job at all. And well, what are we left with? Well, we have a improperly represented modal structure and we're going to miss some things. So if you had known about that change in the modal structure, you might have said, well, let's move the points in a different way, like that. Let's start packing them up near the surface. And all of a sudden, your representation of those modes looks pretty good. And the nice thing is we can actually do this with the IL algorithm. So with some knowledge about what's going on with the modes, we can actually move our grid points so that in the regridding phase, we put them in the right place. And so that's the concept I'm chasing here. So that's what I mean. We can move the grid to improve our approximation to the true modal solution. And that's taking advantage of this regrid step, which is unique to ALE. We could not do this previously in an Eulerian coordinate, but now we can. And so this sort of evokes this idea of adaptive mesh refinement, which we don't really use in ocean modeling, but it's popular in some other fields. And of course, in our case, we're just thinking about the vertical grid and only in the context of our baroclinic modes. So what's the rationale for doing this? Well, I really like these parables from the Kyle Stewart's paper in 2017, which also sort of inspired me to think about this problem. The primary purpose of the vertical grid is to resolve the vertical structure of the horizontal motions. And the second one, the vertical grid should be designed to resolve the baroclinic modal structure of the highest mode supported by the horizontal grid. So what does that mean? So for example, in looking at this figure here, when we tend to think of like, okay, are we resolving turbulence, or how well are we resolving our modes? Normally we think of it in terms of the horizontal grid resolution. And it's pretty obvious as you look at this panel from the bottom layer to the top, higher resolution gives you more stuff. And that's obvious. But sort of the subtext there is your vertical grid has to sort of be, it has to support whatever horizontal, whatever the horizontal grid needs to resolve. So you have to think about the vertical grid too. Okay, so for this algorithm I'm proposing, there's sort of two independent and complementary ways I'm thinking about this. And this is inspired by Jeffrey's paper from 2 years ago. You can mess with the coordinate system, and you can also create sort of an optimized grid in that coordinate system. And so I'll tell you about what that means. So first way, transformation of coordinates. So we're thinking about this in terms of just our spam, sorry. Think about this in terms of our linearized set of equations. We plug in some wave solutions and we get our standard eigenvalue problem. So G is the vertical structure of the eigenmodes, K is the horizontal wave number, and your eigenvalues would be the frequency of those modes. So Jeffrey pointed out in his paper that solving that eigenvalue problem can be prone to error whenever you have rapidly oscillating eigenmodes. So basically wherever n squared is large, like in your picnic line, where it's really important to get the resolution right, that's where it struggles the most. And so one idea that he tried out in his paper, but obviously not in the context of making a new grid, he was doing it for another reason. One idea he tried out was to say, let's use a stretched vertical coordinate to space out those parts. So essentially, rather than using Z, I'll use S, which is essentially a vertical integral of the Brunt-Väisälä frequency. So schematically, it kind of makes sense. So let's, for example, take this idealized vertical stratification profile, and let me break up this profile into 3 regions. We have this blue region, which represents the sort of unstratified part at depth. We have an orange region, which represents the unstratified region near the surface. And then let's call this really highly stratified picnic line region pink. Okay, so in Z space, the blue and the orange take up most of the space. In the S coordinate though, pink now takes up most of the space, right? Because it's weighted by n. So if we were to create a vertically or a uniformly spaced grid in this S space, and then map it back to Z space, that grid looks like this. So notice it packed all the resolution into the picnic client right where we want it. Right, so that's idea number one. Two, what kind of optimal choices could we make for that grid? I mean, we aren't necessarily stuck with using a uniformly spaced coordinate. We can do whatever we want. So again, for example, take this profile event on the left, and let's say, okay, well, we start with eigenmodes, which are orthogonal and have these nice properties. We don't necessarily have to stay in eigenmode space. We can actually project those onto, say, a cosine basis, which consists of cosine waves up there on the top right, or we can also project them on the Chebyshev polynomials, which Jeffrey did in his paper at the bottom there. And if we think about it that way, we have multiple choices, right? Because if you look at those cosines, they're, I guess, what you call curvature, or their profiles sort of vary consistently no matter where you go, right? So that would be a case where if you space out your points evenly, you probably stand a good chance of getting a good representation. Whereas if you look at those Chebyshev polynomials on the bottom, they're varying somewhat slowly in the middle of the domain, but then all of a sudden near the edge, all of a sudden it shoots up really quickly. And so in that case, you can actually show that the best way to resolve those is what's called a Gauss-Lobato grid, where essentially it's what would happen if you evenly space points around a half circle, see it there in the bottom left, and then projected them down onto the plane. So you can see that tends to pack the resolution right near the edges, where it matters the most. And so essentially what I've wanted to do is, between this new coordinate S and this optimal choice for the grid here, you can cook up an algorithm. And so that's what we have. So the algorithm I started thinking about was, during the regrid step, you can calculate n squared at each layer, calculate this new coordinate by essentially taking the cumulative sum of n as you go up through the column, create an evenly spaced or Gauss-Lobato grid on this new coordinate, and then map it back to Z. So that's the core of the algorithm. The reality is, over time and over some experimentation, that didn't work out super well because, in our ocean models, there's other things we need to resolve, such as surface stresses and overflows and things. And so what I'm proposing and what I'll show is you essentially take some fraction of your points, prescribe them in a fixed, essentially backbone grid. So for example, a Z star grid, that those points are always just stationary, and they're giving you the resolution you want near the top and near the bottom. And then you take some fraction of the remaining points, or say all the remaining points, and let the position of those points be determined by this algorithm I had in the previous slide. And so I'll point out the nice thing about this is, for one, obviously you're getting the resolution you want with this, what I'm calling the Stewart points. You're making sure that you're getting a highly resolved surface, boundary layer, and some resolution at depth. But also you have these points that are moving around with n. So as the season changes and maybe your picnic line is moving up or down the water column, your resolution's following it. And so you can imagine there's probably places where that's really useful. And then I made one other modification, which is, rather than using an S coordinate that's proportional to n, I'm using an S coordinate that's proportional to n to the alpha, where alpha essentially controls how tightly packed your resolution becomes when n becomes large, which I found very useful too. Okay, so we tested it, or tests are ongoing. We're using GFDL's OM4 configuration, quarter degree ocean sea ice. I've done a 10-year spin up plus 10 years of output. And so we're going to look at 10 years of time average output, and we're going to take a look at different variables. And we're comparing against a control coordinate, which uses the hybrid sort of isopycnal Z-star coordinate that Alistair showed in his paper a couple years ago, and testing against our new grid. Okay, so the purpose of this grid was to hopefully increase the resolution of your baroclinic modes, which to me meant we were going to get a lot more EKE. Everyone make their guess about how much extra we got. And the answer is we dropped our global EKE by 13%, which just totally blew my mind. I'm still trying to figure out why. So looking at these two grids against each other, so the left is the new grid, right is the control grid. Yeah, there's obviously less intense red regions. So yeah, we reduced our EKE, which was interesting. So what happened? Well, if you look at where the changes happened, it seems pretty obvious, or not super obvious, but if you look closely, we ended up reducing the EKE in the intense currents, so like the ACC and your western boundary currents, and we greatly increased it throughout the quiescent regions. So that would be the center of the gyres, the Arctic, and some other areas. So that's interesting. So what did it do? Well, if you look at observations of where the EKE is distributed, they're on the top, and compare it against what our two grids look like, well, things kind of look interesting. So for example, the distribution of EKE in the ACC in observations is pretty narrow. It's not this like wide, intense thing. It's narrow, and it tends to be concentrated on these really, on these hotspots, essentially. Using the new grid, all of a sudden it got narrow, and it started to concentrate the EKE on those hotspots rather than the hybrid grid, where you can see it's this really broad region of elevated EKE, and the hotspots aren't quite as obvious. Looking at the Kuroshio, in observations, the eddying region in Kuroshio extends pretty far out in the Pacific, and with a cosine grid, or with the new grid, it does now, as opposed to in the hybrid control case, where the EKE is really sort of tightly packed against Japan, and it's also just really, really intensified there. And lastly, looking at the Gulf Stream, in observations, the Gulf Stream EKE region sort of extends about halfway into the Atlantic and then bends northward. It looks like the new grid's starting to do that, whereas in the control grid, your EKE stretches all the way across to Europe and then even beyond. So that was interesting. You can kind of see the same thing in the SSH variants. So our new grid up in the upper left, sort of intensified about halfway across and then starts to head north, whereas the control there in the bottom left goes all the way across the Atlantic. The Gulf Stream separation all of a sudden got pretty good, right? So on our new grid, it actually peels off at Cape Hatteras and starts heading east, whereas in the control, it goes too far north, which is sort of a well-known problem. And to go along with that, magically, the sea surface temperature bias in the Northeast US and Canada all of a sudden looks better too. So for example, because the Gulf Stream tends to detach a little bit too far north, that tends to give a pretty strong warm bias there. And it looks like that has maybe been reduced or eliminated by this new grid. However, just because you can't win them all, did not seem like it improved the notorious blue blob of death out there near the Grand Banks. But yeah, the new grid, well, it does stuff. So we have this partly fixed, partly dynamical idea for a grid. It currently uses Z-star for the fixed backbone part of the grid, although there's no reason why you couldn't use hybrid as your backbone and then have these other floating points that you can, put wherever you want. Again, the sort of underlying concept is that these moving points are based on a stratification weighted coordinate, so it'll tend to follow your picnic line throughout what seasons or locations. I'm still trying to wrap my head around what happened in those simulations, but obviously this is really new. I mean, those results came out last week, and so I'm continuing to test this out, and I'm sort of thinking about doing a high-res like regional test case, or I'm open to suggestions about other ways to evaluate this. So yeah, that's it. So thanks.
Thanks, Scott. Your audio held together. The volume was up and down a little bit, but
oh,
we're good.
okay, great.
Okay, questions. There's several up here. Bob.
Thanks, Scott. I really enjoyed that talk, but it raised two questions in particular for me. One of the metrics we have used for our global models is how well it preserves water masses. Do we see an erosion, for instance, of the main thermocline? And a nice plot that we've often used is kind of a time series of the drift as a function of time and depth. And so it shows up differences, for instance, between MOM6 run as a Z-star coordinate model and MOM6 and a hybrid coordinate model as a huge win. Do you have a sense of whether your vertical grid, which is optimized for the dynamic modes, does a good thing, or does it have offsetting liabilities when it comes to the preservation of the water masses?
I do not know. Again, like these are all very, very new results, but that's definitely something I should look at. Okay.
And then the second question, you've talked about things in the vertical, but if you have differences in topography, say you have a seamount, an isolated seamount, and you do the modal structure calculation over the seamount, that can give you a really different structure than for the adjacent point that is in a trench, say. Did you have to do anything in the horizontal to reconcile where you're putting the grid points in adjacent or nearby water columns to make it work?
Yeah, so one thing we found we absolutely could not do was exactly like what you're talking about. If you have a really shallow area next to a really deep area, that makes a mess. If you just say like, okay, I'm going to put 75 points in the shallow and 75 in the deep. So what we did was basically I have I don't know what you call it. I reduce the number of grid points you use as it gets shallower, effectively. So for example, if you have like a 100 meter depth, you may give it like, I don't know, 10 points, and then the rest of them are just vanishing at the bottom. So in that sense, it's kind of similar to how the Z-star coordinate works.
Thanks.
Steve?
Thanks, Scott. This is really creative. I like it. One of the things that we did in the Stewart paper, I was part of that, and that we saw, which was really intriguing, was changing in the overturning circulation, in particular in the AABW cell. And we had some hand-waving argument for why we might expect better representation of vertical structure to give you better overflows and better overturning circulation, but we really didn't nail the story as far as I know. Do you see any changes in the overturning circulation of any note in your results?
I haven't got there yet, but
okay.
Definitely get that.
Yeah, it's something to look at.
Thank you.
Okay, Deepak.
Thanks, Scott. That was a great talk. And so thinking about your testing ongoing and high-risk regional test question mark, I was thinking a good metric might be these wave number frequency diagrams that Tom Farrar makes for the equatorial ocean, because I think his conclusion was basically in the SSH, you can see peaks exactly where the flat bottom modes, exactly where you would expect from flat bottom mode theory. And then also, add in the meridional structures. So I'm wondering if that's a good metric, even at the coarse model.
Sure. Yeah, I'll look into it. Thanks.
Okay. Any other questions for Scott?
Yeah, I had a question.
Okay.
This is Bob Helper, by the way. It says that partly dynamical and partly fixed, your vertical coordinates. So what does it mean partly dynamical? Is that just the adjustment after every step, or is the target grid fixed?
No, the target grid is not fixed, and that's what I mean. So
Okay,
basically,
okay.
figuring out what your stratification profile is at every time step and then moving points accordingly.
Okay. So, I guess it's currently based on the Z star. So it's, all right.
The
guess
fixed
that's a little-
grid is based on Z star. The dynamical
Oh.
grid, not based on anything. Well, stratification.
Oh, okay. So it's in some regions of the ocean, it's actually fixed. You're only making the dynamical adjustment in some areas. Is that right?
I'm at any given column, I'm taking some points as fixed, like they're always in the same spot essentially, and then some other set of points I'm letting float.
Okay. Yeah, that's neat. Thanks a lot.
Thank you.
Okay. Deepak, did you have a follow-up or is your hand just still up?
All right, I'll take it down.
Okay. Mehmet, quick question.
Quick, sorry. I was wondering, your control simulation shouldn't be the Z-star quarter degree rather than hybrid quarter degree.
We're using the the one that comes in Mom6 examples, which I thought was hybrid.
Yeah, but since you're based on new grid is Z-star backbone, shouldn't your control be the Z-star fully?
In this particular, actually, Bob or Alistair, could you help with this? I don't think they have the Z-star OM4 available, do they?
It's not checked in as an example. We could probably dig it up somewhere. It's been years now since we ran it, but it was used in the papers that Alistair used to describe the original version, and it was that comparison of Z-star versus hybrid that was at the heart of a lot of the.
Yeah, I'm wondering if the key is lower in Z-star already rather than your version of the code. That's why.
Okay. Good point. All right, let's move on to the last talk of this afternoon, and that is Keith Lindsay. Keith, you there? Here he comes. Whoops.
Just a sec.
Okay.
Having problems sharing. There we go. I couldn't find the PowerPoint on the share. Okay. Set show. Okay, very good. Thank you for letting me share this work with the working group. So I'm going to be talking about looking at diagnostics in MOM6 in consistency of tracer budget terms when looking at non-native grid output. And this is work in progress, and this has been done heavily in collaboration with Andrew Shao. So I take blame for any misunderstandings here in the work, but I've gotten a lot of help from Andrew in helping to understand MOM6 as I've been working on this. So, you just can't really talk about diagnostics just as an abstract, here's how you do diagnostics. I tend to think of it in terms of, well, what's the application of the diagnostics that you're looking at? And for me, what led me in this work to dig into these is my work that I've been doing with a Newton-Krylov based solver for tracer spin-up and looking at MOM diagnostics for the preconditioner in that solver framework. So I'm going to give you a slight bit of background on this motivating application. So the first part is that the Newton-Krylov spin-up is operating on tracers as they appear on a fixed Z-star grid. And the main reason for doing this is to ease the computation or interpretation of a difference of the tracer at the end of a run minus the tracer at the beginning of a run. And that's what the Newton-Krylov solver is trying to do, is minimize that difference. And computing that difference, if you've got vertical coordinates that are varying in time, that tracer end and tracer begin are on different vertical coordinates, there's some ambiguity in computing that difference, but that goes away if you treat both of them on a fixed grid. If you go through the machinery of setting up the Newton-Krylov solver, in the Krylov step of this, there's a preconditioner to enhance the convergence properties of the iterative method. And the formulation of the preconditioner that I'm using is based on terms of the form that are the partial derivative of a tendency with respect to a tracer value. And this is for all of the different tracer tendency terms that show up modifying the tracer during the evolution of the model. And this is looking at both of these as the tendency and the tracer on this fixed Z-star grid, which is usually going to be different from the model grid. The way that those are computed in practice, that I'm computing them in practice, is applying impulses in an initial condition on a Z-star grid. Then the model interpolates that Z-star profile to a model grid, runs forward in time, and then I can get diagnostic output back on that Z-star grid and look at the tendency diagnostics along the way. And this allows me then to have the goal is to have consistency between those tendency diagnostics across the evolution of the run, that are wanting them to be consistent with the tracer state at the beginning and end of the run. But things didn't work out quite as I expected. As I started digging into the details of applying this to an age tracer, I wasn't really seeing some of the basic properties of the diagnostics holding up the way that I was hoping they would when evaluating them on non-native grids in the output, particularly on a Z-star grid. So the sorts of features of the analysis that I'm looking at, I'll simplify it a bit and just look at thickness itself. And that has fewer moving parts than tracers that are evolving through the run. And a couple of different aspects of the tracer budget that hold on a native grid and you also want to hold on a non-native grid are the following. The first is that you can decompose the tendency into terms that the tendency is composed of. And for thickness, these are the variable names in the MOM diagnostic output, that you have variations in thickness from boundary forcing, from the vertical remap step in H, and also from dynamics. And that holds on the native grid. And when you remap, it's desirable to have that relationship hold as well. If you're looking at a Z-star grid, or if you're looking at a row density grid, for instance, in your diagnostic output. Another property is to make sure that, as I'm looking at the Newton-Krylov solver, I'm looking at a end state minus beginning state in relating that to the tendency terms. And so you want to have this integral relationship hold, that the time integral of the tendency term is equal to the difference of the variable being integrated. And if you divide this by the length of the integral, the length of the time interval here, then this is also saying that the mean dh dt, the time mean, is equal to a finite difference of snapshots of h, where h is the layer thicknesses. So I'm not going to go into the details of the model configuration that I'm looking at, but I'll just say it's the sort of the NCAR configuration of physics run at 2/3 degree model with a hybrid vertical coordinate, and I'm looking at daily output very early in a run. So there's lots of transient behavior going on, but seeing the consistency holds whether you're looking at a run that has spun up or a run that is early in the run. The key thing here is that it's daily mean instead of snapshot. So here I'm looking at just a single column in the North Pacific, and in the left column is what the absolute value of DHDT with a log scale is. And then if I reconstruct it by those 3 different terms and subtract that from DHDT and take the absolute value of that, you can see from the horizontal scale that we are many orders of magnitude smaller in the error than we are in the term itself. So this is round off error in reconstructing in the native grid with these daily means. So this relationship holds well on the native grid. If we look at different grids, and this is here looking at a density grid and looking at the same terms, we don't have nearly as many digits of precision, of accuracy in this reconstruction. So the error in the reconstruction with these different terms, with the configuration that we're using at NCAR, this is order 10 to the minus 11. So we're getting like 4 or 5 digits of accuracy instead of the 14 or 15 digits accuracy that we get with the native grid. And if we look at a Z-star grid, we're only getting 3 or 4 digits of accuracy. So something's gone a bit off the rails in terms of having these relationships hold. I should say that some of these discrepancies are specific to the NCAR configurations that we're using. There's a analysis workbook that Steve and Graham McGilchrist have put together looking at tracer budgets. And these relationships that I'm showing have a mismatch, hold well in the OM4 configuration. But if you change some of the settings from the OM4 configuration to be the same that we're using in the NCAR configuration, some of those things that agree well start to disagree, like I'm showing in these plots. And similarly, if I try to construct that mean DHDT from the snapshots, H at the end of the day minus H at the beginning of the day, I'm really not getting any digits of accuracy. If I look at that on the Z-star grid, the error is of comparable magnitude to the change in H itself. And this was something that notebook in the analysis workbook didn't even go into. And I'm not sure if this works in the OM4 configuration. I suspect that it doesn't because of the work that the equations that I'm going to show here shortly. So I started talking with Andrew about, well, what's going on? And Andrew described to me why he thought that these errors were unavoidable, but they try to configure the construction of the remapping so that the errors are small, but some errors are unavoidable. And we talked about it for quite a bit, and I didn't quite understand all of the arguments that he was describing. So I decided to set out to convince myself that this was an unavoidable issue, or figure out, if it's not unavoidable, can you actually get around it? So here is some mathematical ways of looking at these expressions. So I'm going to consider the tendency of a field F. And the main reason I'm putting this expression here is just so that you become familiar with what I'm using for my notation of time indices, that the tendency at time level n is what gets you from time state variable at level of the tendency. The current approach to MOM6 in remapping this is to apply a remapping operator to the computed tendency, and that is the definition of the remapping of the operator. And now these remapping operators that go from one grid to another depend upon the layer thicknesses of the source and destination grids, and both of those tend to be changing in time. And so there's some choice in implementing this about what time levels you use for the thicknesses going into the source and destination grids for computing this remapping operator. And it's not just time levels, but it's different sub-steps within the time step of MOM. And in my conversations with Andrew, what it sounds like is there was a fair amount of discussion about how to do that in a way that reduces the errors in this remapping step to maintain consistency in the output. And choices were made based upon experimentation and looking at results. So this is stating that again, the difficulty arises in choosing the time levels for the thicknesses that are used in these remapping operators. If you generalize this a bit, what you can do is consider remapping operators on the different time levels of the field, instead of just applying one single remapping operator to the tendency term, but consider having different operators on both levels of the field. And one of the reasons that I consider doing this is that, in going back to what I was talking about for the motivation of the Newton-Krylov application, where computing an end state minus a beginning state, it's complicated to interpret that when they are on different vertical grids. The same thing applies when you have the fn+1 minus fn. Those naturally have their own vertical grids that they rely upon. And so I think that highlights the difficulty in choosing a single remapping operator for applying to the tendency, is that there is no natural vertical grid that you can say that that tendency resides on. And so that's why you sort of get into a bit of a confusion about what linear operator to apply. So instead, what I'm doing here is applying different operators to the terms in the numerator here, where they map to the same vertical grid. And then that difference makes sense on that target vertical grid. And the notation that I'm using here is that the first superscript is the time level of the tendency that I'm mapping, that I'm doing in the analysis. And the second superscript is the time level of the field that I'm applying this operator to. Now, if you add this up for two different time steps, this is just substituting n+1 into this right-hand side and then adding this up. If you want to have the equation 2 that I showed earlier, that the time mean of the tendency is equal to the difference of the endpoints, if you want something like that to hold in this expression, then you're going to need the terms that depend upon fn+1 to cancel each other. So if you want this fundamental theorem of calculus to hold, you're going to need these middle two terms to cancel. And so you need this n+1 L operator to be the same as the n+1. So in particular, what this is saying is that the remapping operator needs to be independent of the time level of the tendency. It instead needs to depend upon the time level of F being remapped. So in order to get that sum to have cancellation of the middle terms, you need to purely depend upon the time level of F, not the time level of the tendency that you're computing. There's more than one way to do this, but one way that works nicely when you start considering multiple processes across multiple time steps is to use the thicknesses just prior to a process being applied when you're computing the operator ln, and use the thicknesses just after the process is applied when you're using the operator at time level n+1. So here it's not just time level n and n+1, but it's the thicknesses within the time step before and after the process are applied. So if you're doing that and you no longer depend upon that first superscript, then you can simplify the notation a little bit and now define the remapping of a tendency to be the linear operator applied to the updated state minus the old linear operator applied to the old state. I've been working on implementing this in MOM6 by introducing a new post-data subroutine that gets applied to tendencies, and that takes multiple time levels of the argument or a new time level plus the tendency that if it's already been computed, and then thicknesses before and after the process was implemented, process was applied. And if I apply this to run the model with the same sort of configurations that I was showing earlier, and now look at a reconstructed DHDT from the different terms in that expansion on a density grid, I'm now getting agreement to round off error. This is 10 to the minus 7 compared to 10 to the minus 22. So we're seeing 15 digits of accuracy in that reconstruction. When you're looking at the change in thickness as evaluated on a density grid, if you apply this to a Z-star grid output, which is sort of the target that I have in mind for the Newton-Krylov solver, we're also seeing round off differences in the reconstruction of the thickness tendency. And similarly, if you recompute the mean tendency of thickness from snapshots at the beginning and end of a day, we're seeing round off error differences compared to the time mean thickness evaluated by the model. So this is satisfying development for thickness budgets. I'm interested in doing this for tracer budgets, but the same equations that I was showing for doing this for general fields applies for fields, not just to thickness. And this is a work in progress. But here is an example of showing the vertically integrated heat content in each layer, computing that from snapshots at the beginning and end of a day, and comparing that to the time mean tendency as computed by the model. We're getting round off level differences between these two different approaches. Well, here I'm showing it for native grids to show that it works for the native model. And then if I look at this on a Z-star grid with the code mods that I've described, we're also getting round off level differences in the reconstruction error. So this works for reconstructing the tendency from the snapshots. So this is working for tracer budgets in addition to thickness budgets. So summarizing this, generalizing the definition of remapped tendency terms enables the reconstruction of thickness tendency by terms, as well as finite differences from snapshots. This holds on diagnostic grids. Reconstruction of tracer layer content tendency from snapshots also works on diagnostic grids, and applying this to all of the terms that show up, for instance, in the temperature budget is a work in progress. Looking beyond the tracer budgets to other aspects of this that I'm going to need to accommodate with the application that I have to the Newton-Krylov solver is what happens for terms that are not just the layer content tendencies, but relating those to lateral fluxes through the divergence operator. And a natural question is, can lateral fluxes be remapped to diagnostic grids and be consistent with the divergence operator on the diagnostic grid? And we're not sure if that can be done consistently. There's still some math to work out for that. But that will, hopefully we'll report on that sometime in the future. So thank you for your attention. I'd be happy to take questions.
Thanks, Keith. Steve Griffiths.
Keith, this is really nice stuff. I'm very much in favor of this. I'm hopefully you can get this into the main MOM code soon, because I know the whole community would make use of this. For your last bullet here, your aspiration for the last bullet, if you are trying to do that with neutral diffusion, just remember that the neutral diffusion fluxes in MOM 6 are vertically non-local. So they're reaching from one grid cell to a vertically non-local, horizontally adjacent grid cell. So it's going to be tricky.
I fully appreciate that. Thanks. Well, thanks for your comments. And yeah, I've had lots of, Andrew's familiar with the neutral diffusion code. And and he and I have chatted with this considerably. Yeah, I appreciate that. the non-locality of that does present some challenges that we will need to deal with.
Thanks.
Bob?
Yeah, so this is a little bit the same point that Steve was making, but one of the things we found, we just couldn't work how to do it for these neutral diffusion fluxes. So instead, what we're keeping track of is the convergence of the fluxes. And then if you really wanted to work out the fluxes, you would have a three-dimensional elliptic equation that you could solve. You know what the divergence is, you know some boundary conditions, and you can work out fluxes that are consistent after the fact. It may be that a similar approach of keeping track not of the fluxes, but of the convergence of the fluxes, which are now right back at the same tracer points that you're working with. And then you can do the elliptic equation on, say, your Z-star grid after the fact to determine the fluxes. You know, break it down into a velocity potential and a stream function. You know, so maybe an approach that kind of circumvents this whole question of trying to define what the vertical grid is at the tracer point for lateral fluxes where it may not be very well defined. We know exactly which layer it goes from where to where on the native grid, but in the vertical, that seems challenging.
Yeah, I think it is. And yeah, casting that as the elliptic problem from the divergence that on the Z-star grid, yeah, that's an approach to consider for sure. Thanks for mentioning it.
Okay. All right. So, Alistair.
Hi, Keith. I mean, I think this is great that we're tackling this problem finally. I literally had a conversation this afternoon with somebody asking about W, how to diagnose W, which comes up a lot. So I think you're going to basically tackle all of this for us. I was just thinking, the way you presented this in terms of applying the operator to two parts of the time derivative. So you have L in the future and L in the past. I mean, that was the insight. I think it's brilliant. So if you're applying it to something like the divergence of horizontal fluxes, is there a need for the operators to commute and be associative and so on? Is that where we're going to run into trouble because we don't necessarily build grids that do satisfy that? I'm just thinking, because in the vertical, in time derivatives, we've got one column, but I'm just thinking about in the horizontal whether we're breaking anything there. I feel like your approach is going to, if we don't violate any of the ability to rearrange operators, feels like it's going to solve all of our problems. I'm just asking the question whether it does, whether we can put L inside of div.
I don't know yet the answer to that question. That my initial leaning towards what I think might be a solution to this is I think that a challenge with what to do with the lateral fluxes is that the fluxes are on the cell faces. And the problem is that the cell faces have their own vertical grid that's different, and thinking about the vertical grid of the faces compared to the different vertical grids of the cells adjacent to those faces. In one thought that I'm trying to pursue is consider those lateral fluxes on the face from two different perspectives. One is from remap it twice, once using the vertical grid of, say, the west cell, and remap it with the vertical grid from the right cell, and get two different remappings of that. One that would be consistent with, and then apply the divergence operator on one uniform grid for a tracer grid. But if you're applying that to the neighboring column, you would need to have remapped that lateral flux to the vertical grid of that neighboring column. So even though it's one profile of lateral fluxes, I'm pondering actually remapping it twice to both neighbors' vertical grids. And then it looks like you're differencing things on the same grid. And then you might be able to have it consistency with the operator, the divergence operator inside the remapping. So I think you might get commutativity that way, but I haven't worked through all of the math yet to convince that's my hunch of something that might work, but I am not sure. I haven't worked out all of the details to see if it does work in practice.
Very good. We'll leave you to it. Solve the problems for us.
Just to follow up on that point, if I could, Keith, that's exactly what we ended up doing. And Andrew Shao is the lead author of this for these non-local rotated quasi-neutral fluxes. It's basically you have two completely separate remappings of the fluxes to these two different cells. And so things, you can't say where they live in the middle, but on each cell it's well defined. So that worked out well for the things that Andrew did. So that seems like an idea worth pursuing.
Okay, thank you for mentioning that.
Okay, well, good. Thanks, Keith. So we have some time on the schedule for additional discussion and questions. Are there any questions following up from talks earlier today? Okay. Bob? Is your hand still?
Yeah, no, this is a new question for Ian Grooms if he's on. I'm not seeing if he is.
I think Ian had a faculty meeting this afternoon, so you might have to catch him tomorrow.
I'll catch him tomorrow. It had to do with the energetic consequences of these small scale things, the kinetic energy contribution of the Bernoulli function. But I'll ask it tomorrow.
Bill?
Yeah, I have a question for Ian too. So when you get him, let's catch him sometime. But in the meantime, going back, is Scott around? I mean, I remember these vertical grids and resolutions and everything. And at one point, there was a hope that somebody would undertake a Herculean calculation of sort of a really high vertical resolution grid that you could use as the target. Is that ever been done, or does that create more problems than it's worth? But I mean, what do you really compare to? And I'm going back to these compensating error issues and stuff like that. So just on the vertical grid itself, is there a target, or are you just, are we still stuck?
Scott, do you want to respond?
I don't know. I don't have an answer for that.
We don't have a solution is the short answer of some ultra high resolution, vertical resolution grid in our suite. I don't know about GFDL or another group.
So we don't, but I suspect that one of the challenges, if you did do that, you would want to make sure that your grid cells and adjacent columns are reasonably well aligned. There are a lot of places where we approximate horizontal gradients along layers, and if you had really fine vertical resolution and then displaced the water columns relative to one another, that could be problematic. But apart from that, I don't see any reason why this couldn't be done. We run with crazily thin layers in parts of the water column all the time, and everything, the numerics are all designed to handle near vanishing or vanishing layers. The expense and then keeping the grids aligned in adjacent columns would be the challenge.
I remember a few years ago, Steve Yeager ran some nice studies with POP, adding vertical resolution and seeing some impact on tropical circulation. Something like that might be of interest again with MOM6.
Yeah.
And it seemed that the tropics were a good place to look because you could run short enough and see a robust difference in a core or a JRA sort of experiment.
Mm-hmm.
I don't know that those were ever published, but I remember a CESM presentation from him that I thought was really cool.
I can't remember. It's like maybe CCSM 3 era.
Yeah.
Steve's probably on, but my recollection was that the vertical resolution, the model had higher sensitivity to the range of vertical resolutions explored than any of the parameterizations we were considering at the time.
Yeah.
So, yeah, so I think that's a worthwhile endeavor. Let me, there are other questions for related to talks today. So we have these discussions scheduled the end of each of the 3 days, and I don't, this is kind of a rare opportunity for us to sort of speak interactively as a working group. So I don't want to just let the time go. So let me ask, basically give people some homework to think about what are the most important things for us to be talking about and deciding as a working group over this week. And just a couple, just a couple things that came to my mind during lunch today were, I know there are not a lot of people in the CESM community working with Mom 6 yet, but the question for you as a group is, are our training resources sufficient at this point, or do we need different or enhanced training resources for you to be able to start using Mom 6 within the CESM framework over the next months and years? I mean, this will, the intention is this will become the ocean component model over the next development cycle. It is basically our development platform right now. And what do you need in the way of information from us in order to get moving? We have some things out there. There's a Mom 6 manual that's proceeding sort of incrementally. We have a forum on the hosted on the CESM website. We have archived webinars from our working group meetings a couple of years ago that give some background on the model architecture as well as configurations used in different groups. We're trying to include more and more Mom 6 content in the annual CESM tutorials. Is there something different or something that we should be emphasizing within those things? It's another question I'd like to get some input on. Within our the limited human resources we have within our group, we can't work on every possible configuration of the model simultaneously. So the question is, our target configuration that we've sort of speculated would be our workhorse. We speculated a couple of years ago. We speculated this was a useful target resolution was at the higher resolution end of the fully eddy parameterized regime, about 2/3 degree. And that's what we've been calling our workhorse resolution. Is that the right target? Should we be thinking about going up or down from that? If other than a workhorse resolution, what other resolution configuration should we be targeting for our next development effort? We still have a fair bit of work, as you saw today, to get our workhorse resolution tuned and working acceptably in a fully coupled configuration, which is our highest priority. But what are the use cases in this working group that we should be setting up other alternative configurations for? So if people have comments on those questions now, great. Otherwise, think about these questions or add additional questions over the next, for tomorrow and Thursday's discussion session. Bill, did you have a response to that, or? Gokhan?
Yeah, I was just going to add one more item probably on the discussion topic list. As we get sort of closer to running MOM6 configurations within CESM, especially with the spectral element dynamical co-evaluation. I'm just wondering whether we should start paying more attention to model optimization, so that to the extent possible, if we can reduce the cost in collaboration with GFDL or other MOM6 partners, that would be another, perhaps a discussion topic, how to go about it.
Okay. All right.
So one of the things that's kind of looming over all of our heads over the next couple of years is the question of whether we're going to be using the same kinds of computer architectures that we have access to now. It's been a kind of a lurking boogeyman out there for a few decades now, but maybe it's actually getting closer. I know that our limited attempts to try to get things to work well on a GPU heavy machine showed that it's not quite so easy as might be anticipated. But it's also something where I know that there are some folks at NCAR that are actively exploring it and sometimes finding some luck on some machines, sometimes finding that there are unique challenges, especially given some of the nonlinearities and the logic that goes into these Lagrangian vertical remap type models. I'd be interested in hearing whether there are people who are actively working to explore the deployment of these models either to the cloud or GPU heavy machines or things that are rather different than the sorts of machines that we've been fortunate enough to work on pretty regularly for the past, say, 20 years.
Okay. Let's see what we can find out. Gokhan? I was going to ask Gokhan or Alper if they want to.
Yeah, I was
quick summary of what you know of is going on in Sizzle or in CSEG.
CESM is increasingly under pressure for GPU applications. And we are essentially, I mean, we have, for the CSM strategic plan, we have a section on GPUs. We are initially targeting some sort of hybrid applications, perhaps running the actual physics part of the code on the CPUs, but maybe for diagnostic applications and all that stuff, running it on the GPU side. So that's sort of a hybrid application. That's one thing that we are pursuing, but there's also sort of a push towards perhaps targeting certain physics applications that may be heavy on the CPU side. Can it be GPU-fied? But as you know, it's not as simple as, I mean, we can do the Sizzle also is considering perhaps just taking not necessarily shooting for optimized GPU code, but maybe OpenMP directives, or what is it called, OpenACC directives, making it as easy as possible in terms of coding. But I think one of the criticism areas is essentially lack of GPU work on MOM6. So perhaps over the next few years, there's also another big effort. I sent out that new NVIDIA effort within the US that's essentially targeting full GPU applications. So I don't know whether CESM will be eligible to run on that machine, but that may be one of our applications for high-res simulation. So that's, I think we may need to do some concerted effort on the GPU path.
So our experience, there was a NOAA session about a year ago that tried to look at porting things to GPUs. And what we chose to, a group of us from GFDL spent over a week doing this, was to try to work on the vertical regridding part, exactly the piece that Keith just talked about, figuring that that is the least like a simple matrix multiply of anything we could find with lots of logic that varies from column to column. And we were able to get things so that they were running on the GPUs, but it took more time on the CPUs to package things up for the GPUs and then unpackage it than it would have just to do things on the CPUs. And then the other challenge is that the GPUs have this very narrow sweet spot of needing enough work to make it worthwhile, but not so much work that you run out of memory. And it's not an easy problem, but it is one that might vary with different types of architectures that have different memory availability. So I think our strategy for now is to make sure that we have, first off, really robust testing so that when we're refactoring code, we can detect if we break it. But second, trying to clean up everything as much as possible, document and get rid of excess variables. But we don't see an easy way forward for the combination of the vertical regridding, and then the other thing that's kind of unique to ocean models, we have this barotropic solver that basically you are running a wave equation, a two-dimensional wave equation as fast as you can, and there's just not a lot of work between communications. And our kind of sense on the GPUs is those are the two pieces that are likely to be a particular challenge for deploying an ocean model. And Marshall has a comment on the side.
So Andrew and Marshall talking about coding practice. I think unfortunately Ian's not here. I guess I'm aware of at least one NOP proposal that is, it's not just GPUifying the code, but building algorithmic innovation into the model that is more suitable to a GPU-like architecture. I don't know, so I don't know if Scott might want to comment a little bit on that if he thinks it's of broad enough interest. But I don't know if there are perhaps other NOP proposals that went in to address computational performance issues.
I was going to mention also the new, I think Alistair is aware of that as well, the new LEAP project, which actually focuses on machine learning techniques. But if certain parameterizations can be converted to machine learning, I'm not a believer yet, but if that happens, that may essentially open up some GPU applications of certain parameterizations within MOM as well.
Okay, well, good discussion. Other things, people, sort of broad topics people would like us to see us address. Questions or answers that GoCon wants from us for finishing off the strategic plan or input to the CAB, etc.
Yeah, so just to give you an update, I'm almost done with the strategic plan. I was going to send it out hopefully next week, but I need to run it by the SSC first, and I'm supposed to present it to CAB as well. And all the contents of the strategic plan is based on all the input that you guys actually sent. So that's all sort of incorporated as far as I can sort of manage.
Okay. All right. Anything else anybody wants to bring up this afternoon? Okay. Well, in that case, I think we'll adjourn for the afternoon. We reconvene 9:15 Mountain Time tomorrow morning, virtual coffee, and we have a collection of talks that are, several of which came out of the IHS activity, reporting on that work, high resolution CESM, and then some additional development stuff tomorrow afternoon. So hey, have a good afternoon and evening, everybody. Thanks for joining us today, and look forward to seeing you tomorrow.
Goodbye.
We'll be back on the same link. Elizabeth points out we're back on the same Zoom link tomorrow.